Perfect. Is my sound okay?
Yep, you sound great. Take it away.
Thank you very much. Can everybody see my screen?
Yep, looks good.
Perfect. So welcome everyone. Welcome to qBraid-HAQS. It is with great pleasure that I welcome you all to qBraid. Thank you so much for joining us from around the world. The registration numbers at this point are looking phenomenal. More than 550 people from around 60 countries. Some of you are joining from countries that do not currently have a vibrant quantum ecosystem. And the fact that you find these events like qBraid-HAQS and join them and be part of it, it just demonstrates how human curiosity knows no bounds. We celebrate your enthusiasm and your curiosity and your willingness to help us build this field together. Thank you so much. And before we begin, I would like to thank our sponsors, Amazon Braket and qSteam. Amazon, as you already know, they have this Braket services that we already use for even qBraid. qSteam is an initiative with more than 25 universities and more than 70 professors building coursework for the next generation of engineers and scientists in the quantum field. Thank you so much to all of our partners without whom this event wouldn't have been possible. Thank you for the amazing team at QOSF, MIT IQAC, Womanium Quantum. Special shout out to everyone working at Womanium Quantum. They've been phenomenal. And thank you so much to CQ Tech, Oxford University Quantum Information Society, a few people who put in so much work, Alex, Lindsay, Merlu, Raj, Madalena, Verdun, from Womanium Quantums, from CQ Tech, Mohammed Nasser Taha Abdella, and from QSF, special shout out to Alberto, Bennett Brown from qSteam, who will be presenting today, Michael Brett, and Jordan from Amazon Braket. Thank you so much to Simone, VP of Quantum at Amazon. And if I forgot anyone, I apologize, but that I think I've mentioned a lot of the people who've been super helpful. Thank you to Xanadu as well. They've been super supportive of our challenge, and you'll get to hear from them today. So with that, I want to talk about what is this event about? Why qBraid-HAQS? We wanted to braid the best features of qBraid and to show you the wonderful experience that we can provide to all the quantum software developers. It was our attempt. We've been working incredibly hard for the past couple of years, and we've been thinking about how we can provide the best experience for quantum software development. And this is where you get to see how we bring together a lot of the features that we've developed and we internally like, and share it with you so that you can focus on building the best quantum software out there and doing your best work in the field of quantum computing. And then we also want to listen to you. We've been doing a lot of hard work internally. We want to see whether it clicks with you, whether you like the features. So we're all ears. Please feel free to share your honest feedback, criticism. Internally, we have a culture. We celebrate all the criticism you give us. We welcome all of it. We want to get better. We want to provide you the most amazing experience, take away all your pain points that exist while you're developing the most amazing quantum software. So if you have any good feedback, bad feedback, we're all ears. Please feel free to share any feedback you have throughout the event. We'll be monitoring Discord very closely. And this event is also and it is also an opportunity to give you our vision for qBraid. So we're going to provide you sneak peek to a lot of the cool features that we are hoping to develop in the next 12 to 18 months and beyond. We'll get to share those with you, and that's another place with if you become pro user, we will welcome your feedback. We will listen to you, the features that you do want on our platform, and we'll be happy to prioritize certain features over other based on your feedback. And shout out to Oatmeal for this nice graphic. And so now, before we begin, I wanted to talk to you about the vision for qBraid, what it is and where it is going. So we want to be the platform where you can come in and learn, build, and ultimately deploy your quantum software. The journey kind of started during my PhD, where the thought process was, even if you want to focus on quantum computing software, you still had to deal with a lot of the classical overhead. And that could become unwieldy super fast with a lot of the configurations involved with building your quantum software. There possibly existed a way where it felt like you could build a one-stop platform that takes away all the pain points. And that's essentially what we've tried to do, where we wanted to build a platform that is the easiest and that provides the easiest and the most streamlined access to some of the best quantum computers in the world. And why do we care about the quantum field in general? I think it is one of the very few fields in the world that is still in a nascent stage, and yet has the potential to shape the world we live in. In 50 years' time, there's a very good chance that this would define a lot of the features of the world. And you get to play a perfect role if you start right now. So this event is also an attempt to bring in as many people as possible in the field. And we want to show you what this field can do, provide you the best tools. One more thing I wanted to say was, let me see. Yes, one important point that I like to think about when I think about quantum computing is, currently, if you talk about the number of quantum software engineers in the world, it's maybe less than 10,000. That's like a very small number compared to what would be needed in the future. So a quick Google search gets you the number for classical classical software engineers to be around 21 million. And if you go out 10 years from now and even model 10% of that number working in quantum software, then that's still 2 million people. And we're nowhere close to that. And so this is where we want to build a platform that helps the field scale as well. So while you are starting your journey, we want to listen to your feedback and whether we're providing you the best experience, because your experience is very important as it tells us how we're doing. And we want to make sure that there's a good chance that whatever you're feeling, other people are feeling as well. So please feel free to share your feedback. And now we're going to move on to qBraid platform, what it is, and what are all the features that we provide. So at the heart of our platform is an integrated development environment, and that is highly optimized for quantum computing. And in a few minutes, I'll give you a quick demo, but the idea is that all the different quantum software in the world, as well as hardware, are available, ready to go. All the software comes pre-installed. Access to hardware is available by running a few lines of code, And essentially, what I like to say is we take you from not knowing anything in quantum to running your first quantum program in under 2 minutes on simulator and in under 15 minutes on real hardware. And again, this is like a platform that is built for even super pro researchers and software engineers in the enterprise world as well. In fact, one of our research scientists at qBraid, he published 2 papers recently, one on supply chain management using quantum computers. And there's another really cool paper that should be coming out in the next 2 weeks. So keep an eye out. That addresses quantum power flow, and all the simulations were done completely on qBraid. So it is a platform that is perfect for even software engineers and researchers in the industry. And as I'm going through the demo, you'll see we do a lot of cool tricks where we provide you not only quantum software and hardware, but all the different tutorials from various companies also come pre-installed in your home directory. So essentially, you just log in, open any of the tutorials you like, and you are able to run the code within those tutorials without having to install a single thing or even Python in your computer. And that's essentially the value that we've been able to build. Beyond that, you're able to configure access to quantum computers with a single line of code. And to talk about all these features without further ado, I want to give you a quick demo of the platform. So here we are, and feel free to follow me along the tutorial as I present. So this is our website. You can sign in. If you still don't have an access account with us, it's very easy. You can log in with Google. Once you log in, you will be taken to this account page. And this account page is where we provide you an overview of the qBraid platform. So you can launch various different things from here. You have your quantum jobs, the recent quantum jobs you've run. You've got your courses here. You can access your profile. And it's kind of a dashboard for everything that is possible on qBraid. So first off, we're going to start with Learn platform. So this is where you can see we have a course available. Many more courses are in the works. In fact, we are working with the qSteam team to deploy their courses on qBraid. And hopefully you'll see some courses available publicly for everyone to take. If you have your own course that you've built out of your research or while you work at a university and you want to deploy it for your organization or publicly, please do reach out. We can work with you, and we're happy to deploy your courses on qBraid as well. And this platform, super interactive, where you can come in, you've got a lot of animations and widgets that you can play with for better understanding. Not only that, if you encounter any code snippet, the best part of this platform is you just click play and you run your first quantum program within 2 or 3 minutes of joining our platform. And the idea here is if you understood what just happened, you printed out your first quantum circuit, then you're ready to move on to our next platform called qBraid Lab. If not, we do have an entire course built for you where you can watch video lectures done by Dr. Andrea Coladangelo, who's one of the leading experts in quantum cryptography. And then you can go through different questions and check your understanding with them. Right, so now coming back to account.qbraid.com. So that was courses. We will be deploying a lot of new features. So anytime you have new ideas for what you would like to see in any of our products, please do share them on Discord. We will be watching your comments and suggestions very closely. Then I want to come to the media. And this is where we've made an attempt to build a community around our tools. So we've got blogs, news, papers. So the recent papers coming in the world of quantum computing, if you know, if you're familiar with the field of quantum information, then you know Scirate is a place where most people go to get their latest feed for the papers coming out in the field. And this is where what we've done is we bring you all the top Scirate papers in one location on qBraid itself. So you can come to papers, preview, read the abstract straight from here, click read paper, and it opens the paper. So I was just reading this morning and I realized there's this amazing paper out of the Google team. In the past 2 or 3 days itself, I think this is the second paper that has come out with Google Group and shows the tremendous pace of the field of quantum computing. There's like almost every day, there's so many cool results coming out. So much progress happening in the field. And a tiny sneak peek for this feature. We are in the process of building out functionality that gives you access to building your own library. So essentially you will read and we will allow you to build out your own library of papers straight from this feature. And this is on our to-do list. You'll see it in the coming months / year or so. And then we have events, the latest quantum events you can take, you can be part of. So we allow you to post new events, news that other people can vote on. Eventually, we will build out a functionality of quantum karma. So the number of papers or events or news you submit and how community values your input and what you contribute back, that will count towards your quantum karma. One of the most exciting features, or at least one of my favorite things on the platform, is this blogs feature. So we allow you to publish blogs on qBraid. You can easily publish blogs and you can have code within your blogs. And the best part is when readers are reading your blog, they can play with it. Hello, hackers. And so you can run the code, click play, the entire code runs without any problem, and people can interact with it. So this provides another dimension of like interaction with the content that you're creating. Up until now, most of the content or the blogs that gets created is very static. So this is our attempt to provide you a new dimension of interacting with the content. And as with the Learn platform, you can also publish a lot of widgets where people coming to qBraid, they will be able to play with a lot of the widgets that you publish. So we use standard bokeh libraries and we render bokeh widgets on the front end as well. I'll talk a little bit about the bokeh widgets and a few other things when I'm going through the lab platform. So this is, as I mentioned, all the community building stuff, and you'll see a lot of cool stuff just shows up on your dashboard, like hacks. So we have all the teams registered here, and a big shout out to all the speakers. You'll get to hear from some of the industry experts, what is happening at various companies and how they are thinking about the field. So definitely tune in and hear from Goldman Sachs, Capgemini, Bleximo, Xanadu, BMW, Pascal, DOE, Cold Quanta. And so we have Los Alamos National Labs, Carlton Coffrin, Davide from USRA NASA. So an amazing lineup of speakers who will bring you the knowledge varied from it. And the talks are kind of spread where there's a lot of technical talks, but also more generally accessible talks at motivating people. So please do come to all of the talks. I think you will learn quite a lot. Now, coming back to the main piece of the central element of qBraid called qBraid Lab. This is a platform that is built on top of Jupyter Lab that most of you might be familiar with. And the best part is there's a lot of functionality that may be already known to you. And on top of that, we've built some of the best features that you will find provides you a lot of value as a quantum research person or a quantum software engineer. So let's see what we're looking at. One, you'll see a Jupyter, standard Jupyter interface where you got access to a bunch of kernels. And if you're following along in your account, you may only see 2 kernels, one Microsoft's Q# and Python 3 default from qBraid. Other kernels, I will walk you through how you can get access to other kernels. And so let's get started looking at the features. So first, in your repository, you will see you have this folder called qBraid tutorials. And what we've done in this repository is that we've brought you access to all the different tutorials from Amazon, Google, IBM in one location. You can open any of the tutorials you like. For example, this one, and you just choose Python 3 default, run the code, it goes through, and you're just running the code without any problem. So I understand not all of us would understand what's going on in here, but it's really cool that you do have access to this amazing platform where you can go from 0 to running quantum machine learning code within a matter of minutes. And of course, you can come back. There might be a lot of elements that you do understand, the data, where it's coming from. So you do get like a head start where you can start playing with a bunch of the code. And that has been the main value we wanted to create, where just the same way I showed you this paper by the Google group today with the most cutting edge research, we wanted to reduce the timeline it takes for people to come out with research and the rest of the world to get access to the research and reproduce it. So that is our goal, to reduce the time it takes for people to go from like looking at the research code and reproducing it in their own local environment. So hopefully in the future, we will reduce the timeline to maybe a matter of hours, where if a research piece comes out, you will be able to get access to it within qBraid platform. So not only reproducible code, but also reproducible runtime environment. So now coming back, you can open Amazon Bracket. You have different, and again, you can just start with either Python 3 Bracket or Python 3 default, and you can start running the code and it goes through. Now, what about the quantum hardware? Well, in that case, I want to share with you this amazing extension that we've built called Environment Manager. So if you're following along, I would invite you to click on this, and you will see that we have in your account, you may only see 2 of these environments, default and Microsoft Q#. If you want to get access to more platform or more environments, just click Add, and you'll be taken to a new screen from where you can access new environments. So to get access to hardware, you can either install Amazon Bracket here, or for this hackathon, for all your hacking needs, we've built a HAQS22. So just click on install, and you'll see it comes on the main screen and it says installing. So while this is installing, what I'm going to do is I'm going to use the Amazon Braket environment. And as you can see, we provide a nice functionality to activate, deactivate environments right from your environment manager. So once you have an environment activated, you can get access to the kernel of that environment from this interface. So you select it, and then you can run, and you'll see the code runs for Amazon Braket. And here, the idea is we wanted to provide sort of a sandbox kind of a functionality for each of the SDK available from big companies. So you will find an environment specifically dedicated to IBM Qiskit, Xanadu's Penny Amazon's Braket, and many more. And so you have Pulsar, Quandela, Perseverance. So a lot of these software available in their own sandbox. And then I want to show you how do you get access to your quantum hardware. So again, very simple. With a single line of code, qBraid jobs enable Amazon Braket. You can configure access to quantum hardware. So for me, it says you have already enabled qBraid quantum jobs in the Amazon Braket. So that means that if I run the code to connect to quantum hardware, I will be able to submit jobs to quantum hardware. So let's go ahead and do that. So I'm going to import all the packages that I need, and then I'm going to run the code here. So if this piece of code runs, I would have verified my connection to Amazon servers, about IonQ, OQC, and then Rigetti's M1 device. And while this is loading, I want to show you that with all these environments, these are just your Python standard environments. And you can look at the details of each of those environments by clicking more. You will see all the Python environments, Python packages that you get in a given environment. If you want to uninstall, you can do that. And ultimately, a sneak peek, we are planning to provide you a functionality where you will be able to create your own custom Python environments and share them with your collaborators. And that's the really cool functionality we're thinking of building out, where, as I mentioned, not only reproducible code, but also reproducible runtime environment. So you can go ahead and, close this, and you will see now this piece of code has been completed, and I've verified my connection. I can run it on a local simulator first. You'll see that it goes through. Now I can also submit a job to Rigetti's quantum computer. So here I'm going to be submitting a job to Rigetti's M2 qubit. And so this is where I want to mention a couple of things. One, we are providing you qBraid credits. Everyone who joins this hackathon will get some amount of qBraid credits to connect to quantum computers from Rigetti, IonQ, D-Wave, and Oxford Quantum Computing. You should pay attention to how much it costs for submitting circuits, because that's part of the challenge. So one, we definitely want you to do amazing work towards the challenge, but partly you have to, part of the challenge would be to figure out when you want to use your credits for submitting jobs to quantum computers. And you should pay close attention to how much it costs, because these machines, because the field is so new, the access to these devices is quite expensive. And if you are doing good work, don't worry about it. We will work with you to provide you as many qBraid credits as you need for your challenge or your project later. And so I'm going to go ahead and run this code. And if this goes through, you will see the task would have, the quantum task would have been created and my job would have been submitted to Rigetti's quantum computer. Sometimes it is offline, I want to mention, and it fails, but don't worry about it. Just look at the window in which Rigetti's quantum computer is available, and then you'll be able to submit jobs. So that's another thing you want to pay attention to. Part of the reason why we made the hackathon 2 weeks is because many of these devices have their specific windows during the day in which they're available. So with 2 weeks, you get ample time to figure out when you want to submit jobs, and you get to plan out your tasks. And you can see the status of task. It has been created. And this is the time when I want to show you another really cool extension we built within the Jupyter ecosystem. And this is an extension that we call Quantum Jobs. You can refresh and you'll see that now Rigetti has popped up. You can get the details. You can look at the job ID that I submitted, the device I submitted it to, and it says Rigetti's quantum computer and some more details. So you can track the jobs you've submitted from here, and you can check the status of the job, and it still says, it says completed. So I just completed the task. And if I refresh it, it should say completed. There you have it, right? So hopefully another really cool extension, and you will be able to filter out, for example, for AWS, IBM, and it shows all the IBM jobs I have run and the AWS. And as we launch more providers, we are working with many more hardware vendors. So you will see many more quantum computers pop up in the next 16 to 18 months. And then we can go and run another circuit on IonQ. Let's go ahead and do that. Perfect. So it says queued, and I can refresh and see that IonQ has showed up here. Perfect. So we're going to keep going. This will probably stay in queue. If a lot of you are following along and are submitting circuits with me, you will see that it could remain in queue for some amount of time. It says still queued. We're going to go ahead and submit another circuit to Oxford Quantum Computing's Lucy. And let's see if it goes through. Perfect. It says queued. And I can look at the status, refresh my jobs, and you'll see that both of these things, jobs are being initialized. And then you have code where you can do task recovery. So this is where Quantum Jobs extension will be super useful. You can come in and you can grab the job ID straight from here. And then rather than Rigetti task, you can actually put ARN of any task you've ran in the past, and you can plot it out and it'll get you the results. It says completed. And let's see if it gets the result. Oops. I think I would need Rigetti. Let's see, let's find Rigetti. So if I grab this part, then I should be able to get the results. Perfect. So you can see this is a result of me running a Bell circuit on the Rigetti's device. And you can see the results are here. I only ran 100 shots. So you can run the circuit with 1,000 shots. And yeah. So that's your quick introduction to how to get access to these quantum devices. Little bit more features on the environment side. So if you want to install custom Python packages, you can come to the terminal, and we have our own qBraid CLI, and you can know more about the CLI by typing qBraid-H. And this will give you all the subgroups that you can use. So what you can do for configuring all the Python environments that you have installed on your qBraid lab platform is go to ends list. That shows you the list of all the different Python environments that I have available in my workspace. So if I want to configure a given environment with particular Python packages, what I can do is just do ends, then activate, and then the name of the Amazon, perfect. And then the name of the environment. So if I do that, you will see that I activate the Python environment for Amazon Bracket. At this point, I can just go ahead and pip list. So now this is your usual Python environment that you may be familiar with. And you can do the pip list. You can also pip install stuff. So if there's a particular package that you want, this is the place you would come to install that package. And the same pip list that you see here is also available by clicking on more and available from here. And we do plan to make the functionality available where you will be able to request a new package installed straight from this UI. Perfect. Moving on. So I've covered the environment manager, your quantum jobs, and I want to share now snippets. So this is another really cool extension that we've tried to build. So here you can come, so there's, let's say, a piece of code that you use very often. And this happens with me all the time where I know there exists a piece of code that would allow me to do certain thing, but I just cannot remember. So don't worry about it. All you got to do is come here and search for, let's say, Bell circuit. So you come here, you'll see that there's code contributed by this amazing person. You copy that code, you come to your notebook, let's say, and then paste the code and make sure that you are in the right environment. So let's say Python default, and you're able to run the code. There you have it. And so there's many more snippets available that you can play with. You're also more than welcome to contribute your own. We really encourage you. Again, this is something that will contribute towards Quantum Karma. All your favorited snippets show up here, so you can make sort of like bookmark all of these snippets and get access to them. You can also tag them. So eventually we are going to allow people to tag snippets where they can tag snippets, and you'll see these are all my Qiskit snippets. You can come here and look for circ, and these are all my circ snippets. You can also sort or filter according to different filters we provide here, those favorites and so on. So this is like a cool extension to keep track of. And then we come to Git, really cool extension that allows you to collaborate with your team members. And this is something that I'm guessing you will be using quite a lot as you work through the challenges. So as I go into a Git repository, let's say qBraid lab demo, you will see that I'm able to see all the main branches, tags for a given repository. I can make the changes, push or pull. I can make commits and so on. And the Git extension is also available straight from the terminal. So it's your choice how you want to use it. The UI provides you, as with any UI, like a subset of the features available, but you can always come back and just CD into your qBraid lab demo, and then you can do git status, and git is pre-installed and get access to all the different features that Git provides. So first I want to deactivate so I don't do anything wrong with the Amazon Brockhead environment. So you've got your Git feature here. Another really cool thing that we've been working on and hopefully you would like is if you go to our github.com/qBraid, you will find the qBraid challenges, and we are making public this launch on qBraid feature that has become my favorite very fast. So you just come to a repository that you like, and if it has a launch on qBraid button, you just click on it. It takes you to qBraid, clones the repository, and opens it on the qBraid platform with most of the stuff pre-installed, ready to go. So really cool feature that you can use to get more visibility among the quantum community. So you will see once it loads, you will have qBraid lab demo straight from here. And qBraid lab demo, this is the demo of the lab as well as the custom SDK that we've been building. So this is where you will get to hear more about qBraid SDK from Ryan Hill, who's the CTO of qBraid, and he'll walk you through all the different features that SDK provides. SDK is like a single interface to all the quantum software as well as hardware. And you pick a language that you like, you just specify the hardware you want to run your quantum circuits on, and if there's a mismatch, we transpile your circuits and run on the hardware for you. Let's see. And one more feature that I want to talk about is the blog. Publishing any work you do as a blog is incredibly simple on qBraid. So let's say this is my notebook, I've got text, I've got code in there, and I want to publish it. So you come here to file and you just say publish notebook. If you want to add a thumbnail to it, you can add by clicking on the image, you give it a title, add description, and publish, and then it goes live for everyone on qBraid platform. So I highly encourage everyone joining us. Like if you go through building your own challenges for qBraid, definitely share what you've learned and what new things you've done during the hackathon as blogs for others to learn from your experiences. One more cool thing I want to talk about, and this will be the last thing before I finish up, is we do provide you a lot of cool features. Let me see, it's here, and then iPiBeautify. So you may have heard of this repository called iPiBeautify. So what it does is it integrates JavaScript and Python. So, and we ship this library out of the box on qBraid. So you do get access to buttons and a lot of other really cool features that come pre-installed. And so what that allows you to do is that allows you to build some really cool widgets or interactive functionality from within the qBraid itself. And so what I mean by that is, let's see, is this the one? No. So this is the blog that we've been working on with Amazon team, and you can see that I have a lot of widgets that I can play with. So not only you get to do a lot of quantum computing stuff, but you get to build something that other people can use very easily. So we are always looking for features that we can include within qBraid to provide you much more features that adds value to your clients or your organizations, and of course yourself. And one cool thing I want to talk about before I finish up, just the same way you see environments, qjobs, quantum jobs, stay tuned. We will be launching configurable classical compute as well. And now what does that mean? What that means is that, let's say you are doing a simulation of a quantum circuit and you want access to, let's say, a 50 CPU machine for a couple of hours. And that's where from within an extension, you will be able to swap out your CPUs and even get access to GPUs by a few clicks of buttons, and you'll complete your simulation, switch out the machine for, let's say, back to 4 or 8 CPUs. And essentially, you will be able to get access to scalable compute. And with that, I think I want to finish just one last thing, coming back to my presentation. If you liked what we are building, we are looking for people to join our team. So we are and will be hiring. So if you really resonate with the vision that we have for our platform and you want to contribute towards the field, this is your chance. Please write to us with your resume at careers@qbraid.com, and we would love to chat with you. Thank you so much. I want to see if there are questions.
Yes, thank you, Kanad, for a really fantastic talk. We do have a few questions. I'd like to begin firstly with a question with regards to, you have a background in astro, having done some astro stuff in India. Is it possible to perform multi-physics CFD and other simulations on qBraid?
CFD, computational fluid dynamics.
Yes.
Oh, wait. So maybe I want to ask a question. So are we talking about CFD using quantum computers or CFD in general?
Abdullah, maybe you can kind of mention
Maybe
that.
I can, yeah, maybe I can answer for both the situations. So CFD using quantum computers, that still remains an open and exciting question. How do you use quantum computers for one of the most pressing problems that the world has ever seen, computational fluid dynamics? How do you solve Navier-Stokes? So there have been some recent papers where they propose how you can use a quantum computer to solve certain restricted versions of Navier-Stokes. As of now, we don't know how you can get an advantage solving Navier-Stokes on quantum computer, but it would be incredibly wonderful if we could find some extension. Coming back to, let's say you were speaking about just computational fluid dynamics with no quantum involved on qBraid. In fact, yes, that is possible. I'm pretty sure there are like so many different Python packages that allow you to perform simulation, CFD simulations. And if you want to get access to those and run them on qBraid, incredibly simple, just make a new Python environment, install all the packages, you're good to go.
Great. Next question is, are those notebooks shareable?
Oh, yes. Thank you so much. So right now, we don't have the functionality that allows you to share a notebook with your collaborators. So let's say you log into qBraid Lab and you right click it, share, and it pops up in your collaborators account. That's not there, but it's on our to-do list coming soon. We have part of the functionality I want to share with you where you can come in. Let's say you are reading a blog, you can launch on Lab. So let's say there's a blog that you really like and you want to play with it more and you want to save your progress, just launch it on Lab and it will take you to our Lab platform, open the notebook, and that will remain as your copy. But good question. That functionality is coming. I think maybe this is something we can do. So post on feature requests in Discord. If you get a lot of likes and other people supporting your features, we will put it on our to-do list. So super interested in listening to what you all want and happy to make that happen.
Great. Can you talk a little bit more about the hiring questions? Are you hiring in the US, outside? Do you offer internships? And then
Yes, yes, and yes. So we do hire outside of India as well. Sometimes, given the geopolitical situations, hiring from certain countries is harder than others, but we do make a lot of effort uh, hiring amazing people from everywhere. And then, what was the last part again, Ricky? Sorry, I forgot.
do you guys have internships? Can you guys talk
Absolutely,
about
yes.
what those do?
We do take interns over the summer. In fact, this year we had 3 interns, um, people who did incredible work. You will see, just follow us on our LinkedIn and Twitter. We will start talking about the papers they published over the summer, the really cool stuff that they did. We will try to make all of that, all of their work available on qBraid and work out of the box. So definitely give us a follow on LinkedIn and Twitter, and you will hear about those their work very soon.
Great. I have a few questions with regards to the challenge, which we will get to when Ryan will speak later on in this session. Secondly, I'd like to just kind of discuss a really wonderful question as well that maybe Kanav, you can highlight that Ryan will also talk about. Kareem has asked, excellent work, first time to learn about it, really like how it's unified. Are there converters between different packages like Qiskit and Circ?
Great question. And as you already gave away the part of the answer, yeah, that's the idea with qBraid SDK. You will get to hear about qBraid SDK from the main architect, the man behind qBraid SDK, Ryan Hill, our CTO. He's going to talk about like how with qBraid SDK, we're making an attempt that there should be a unified interface to not only hardware, but also software. There are many things that Amazon Brockhead does well. There are many things that Qiskit does well. And there are a few things where and there's like a good overlap where there are features that both of them do well. And then there's features that this one does well, not that one. And that's where with qBraid SDK, you can get that functionality where pick out the best features without having to learn each of the software separately.
Great. And we have a question with regards to, are you looking for an evangelist? Are you looking for like a community builder of sorts?
Always. The answer is always. I think these tools are incredibly useful only if there's a lot of people using and contributing. So yes, come up with ideas and tell us what you're thinking, and we're happy to chat.
Great. I think that could wrap up some of the questions for now as we transition to Jordan, who will be speaking next. She should be arriving shortly. Then I also want to mention that if you want to be a community manager, we do have a few. Lorraine from Africa, who is part of One Quantum Africa, as well as Alberto from QSF are also community managers, and they kind of manage it. And if you have any questions about qBraid, they'd be always happy to answer. And they should be in the qBraid office hours section as well.
Perfect.
One more question, it looks like. Ryan Chaos from France is asking if there might be missing notebooks from the Pascal and Quandela frameworks. Can they be added on qBraid?
Of course, of course. We're working with both the companies actually. We should be launching. So their software is already online, but their tutorials working out of the box in qBraid tutorials, we can make that happen very soon. Yeah, thank you for the suggestion.
All right. Keep the questions coming. I think Jordan should join, and we'll kick it off with her in 3 minutes. Hi, all. We're still kind of waiting on Jordan, but she should be arriving soon. We're going to double check on her availability, and we'll get back to you guys quickly. Thank you. Hi all, thank you everyone for coming. I just want to say that we now have our presenter from AWS, Amazon Brocket's tech evangelist, Jordan Sullivan, speaking with regards to um, how to use Amazon Brocket and getting started with it and all of its amazing features. So I just want to make sure video's okay, mic's okay, and I'll set you on spotlight and we'll get started. Thank you, Jordan, so much for coming.
Hi, can folks hear me? Is Zoom working okay? Okay, take that as a yes. Alrighty. Very excited that everybody made it, and I'm gonna be talking a little bit about the basics of Bracket. I'm gonna give a little bit of a background on quantum computing as a field and kind of when we have gotten into it. So I will share my screen. Okay, is this showing full screen for people? I'm gonna take that as a yes. Okay. Alrighty, so like I said, I'm gonna start with a little bit of a brief history of quantum computing, and then I'll go into what Bracket is and how you can use it for research or projects like this. So first of all, I like to call this slide from the lab to the laptop. Basically, in the early 80s, quantum computing was first proposed, and it was primarily Richard Feynman who proposed using quantum computers to simulate quantum mechanics. And then it was mid-90s when Shor's algorithm was discovered by Peter Shor. And this is the algorithm, for those who aren't familiar, that allows you with a full-scale fault-tolerant quantum computer to break RSA encryption by factoring very large numbers. Then in 1994, the first quantum logic gate was actually experimentally realized. And then there was a pretty long period from 1996 to about 2013 when there were a lot of theoretical and experimental breakthroughs in quantum computing, which are hard to summarize. So I've just put them all in one category. But then in the early 2010s, you have a lot of different startups being founded and a lot of companies kind of getting into the field. And so I've listed a number of our quantum hardware providers that we have and as partners at Amazon Bracket. Over here. So we have Rigetti, IonQ, Oxford Quantum Circuits, Xanadu, and Quira and Bracket, Amazon Bracket, which is where I work, and qBraid, of course. So that's just to kind of give a sense of where we are in the development of this field. So if you think about the first quantum logic gate being demonstrated here, and now we're kind of in the hundreds of qubits range, that's a sign of kind of how far we've come so far. So what is Amazon Bracket? It is a service that lets you access multiple different quantum computers. So there's kind of a workflow that we typically think about, which is building quantum circuits, first of all. So developing with the Bracket SDK or using qBraid to access Bracket. And you can do this with a Jupyter notebook or a command line interface or your favorite IDE if you prefer that. And then next in our workflow is testing. So this is prototyping your quantum circuits with quantum simulators. So you have a couple of options here. There are a couple of simulators that are free and open source, and you can run on your local machine, your laptop, or computing cluster if you have access to that, like at a university. Or if you have larger scale quantum simulations where you need more computing power, or you'd like to run in parallel, you can use one of our on-demand simulators, which are hosted by AWS, and that is SV1, DM1, and TN1, and those are all 3 different quantum simulators that are useful for different purposes. And so after you have run some simulations and perhaps gotten some insight into what you will be looking for on quantum hardware, then you can run across multiple different quantum computers, as well as leveraging classical compute resources. And the second part is important because at this stage of noisy intermediate scale quantum, or NISQ, there is a very strong need for closely coupled quantum and classical computing resources for hybrid algorithms. Essentially, you are using the strengths of classical machine learning techniques or other high performance computing techniques to improve the performance of your quantum algorithm in the presence of noise. And then finally, the last step in this workflow is analyzing the performance of your algorithms. So you can monitor algorithms as they run, and say if you were trying to run a hybrid algorithm that will eventually, ideally, converge to a minimum value, you can track that with a bracket in near real time. And then you are also able, because it's really just one line to switch between one line of code to switch between different quantum computers in Amazon Bracket, you can in a relatively straightforward way, compare and benchmark different devices against each other. So what quantum computers do we actually have available on Bracket? So first one is D-Wave, and this is quantum annealing. Next is IonQ, which is an ion trap quantum computer. Then we have Rigetti, which is a superconducting quantum computer, and Oxford Quantum Circuits, which is another superconducting quantum computer. And actually coming soon, we have Qira, which is a new type of quantum computer that a lot of you might not be familiar with, but it is a programmable array of neutral atoms, Rydberg atoms specifically. That's a specific kind of excited state that has kind of interesting properties that you can study other physical systems in an analog simulation way. And so that should be coming pretty soon here onto the service. And here I'll talk a little bit more in detail about the simulators that I mentioned. So first of all, the local simulator, this is included in the Bracket SDK, which is open source. And as I said, it's pretty convenient for prototyping and just running small scale quantum circuits that are generally, we say, if you've got a typical laptop, it's around 12 qubits that you would start to run out of memory, because quantum computers and really simulating any sort of quantum system, it blows up exponentially in the problem size. So you really immediately start hitting these very large exponentials as you go above, around 10 to 12 qubits on a typical hardware, but sometimes you can do better than that. And of course, if you've got like a whole computing cluster on your as an available resource, then you'll have better luck there. But one thing to keep in mind is that you can't do parallel computation, so you can't do concurrency with the local simulator. To do that, you would need to use one of our on-demand simulators. And so the first one of those is SV1, which is a full state vector simulator. And so the local simulators, we have a state vector simulator and a density matrix simulator. And the second one of those is for simulating noise. And that one has a limitation of essentially half the number of qubits as a state vector simulator, due to the fact that you are storing basically double the size of a state vector, because that's how outer products work. And so For the state vector simulator, you can simulate up to 34 qubits, and you can do this in a concurrent way. So you can simulate things in parallel, and that doesn't actually change the cost of running it at all. So the next quantum simulator that we have that's on demand is called TN1, and that is a tensor network simulator. And this is kind of an interesting one because it is useful to simulate up to about 50 qubits for certain types of problems that have structured entanglement. And so figuring out which of these to use is a bit of an open problem, actually, but there are some types of structures that we know are amenable to being simulated on a on a tensor network simulator. And one example of that would be like a quantum Fourier transform. And generally you want things with local entanglement. So then the last one is the density matrix simulator, which I alluded to. There's a local version of this as well that you can run, but for the on-demand version, you can simulate up to 17 qubits with essentially studying the effects of quantum noise. You can design different quantum noise channels. Sometimes you might want to try to emulate a particular quantum device. And so this one also, with the previous two, you can simulate in parallel. And again, that doesn't change the cost of running the algorithm. So now let's talk a little bit about the Bracket SDK. So it's an open source Python library that is on GitHub. And as you can see on the right, you can check it out for yourself, just doing a quick search of Amazon Bracket. And so you can use it to design and build quantum circuits. You can use it to submit jobs to quantum devices and monitor their execution. And so here is where we talk about the two local simulators that are included. Those live in the Bracket SDK. So for all of y'all in this quantum hackathon, you'll be using Amazon Bracket with qBraid. And so this is the interface that you'll probably be likely to see. And so it's qBraid up here. And so this is a Jupyter notebook. And without having to set up your own AWS account and do credentials and configuration, a lot of the stuff, qBraid takes care of all of that for you. So you can just get up and running basically right away. And I believe that's all I have. So yes, thank you so much for having me. And I hope you all enjoy your hacking adventures, and good luck.
Thank you so much, Jordan. Thank you for speaking. It was really wonderful to hear about Bracket, and all the time we're so thankful for the support you guys provide us. We do have a few questions, starting off with Kareem, who asks, can we use Bracket with qQuantum? I think this is a NVIDIA provided service. To scale the qubits, mostly on CPU, we can do around 22, but on qQuantum, we can do more than 150.
Yeah, so you can use qQuantum with our hybrid jobs feature, and that would be using what's called an embedded simulator. But I don't think you'll be able to use hybrid jobs for this particular hackathon if you're using qBraid, because it's not a supported feature yet. So eventually, yes, but for that, you would need to be using hybrid jobs.
So thank you so much. Yeah, absolutely. We'd love to have that as an added feature, and we hope to get that going soon. Also, I have a quick question. In terms of the availability for Bracket, is there a way, if you don't have an Amazon account, to just kind of get a feel for it or understand where it is?
So one option is to just pip install the Bracket SDK from GitHub and just play around with local circuits and essentially get a feel for the local simulator. So you can design circuits just fine like that, but you just wouldn't be able to run them on quantum hardware.
Great. Thank you so much. And I think we will keep fielding questions. If anyone else has any other questions, please feel free to mention it, and Jordan will be more than happy to answer.
Yeah, I'm also happy to answer questions that are slightly off topic from the hackathon. If you have any questions about quantum computing in general or careers in quantum, anything like that, I'm happy to answer.
Jordan, I have one question for you actually.
Sure.
What made you kind of take your path to join AWS and become like a quantum tech evangelist? I think it's a super cool role. And then just what I really like is, you get to interface with a lot of these hackathons and people who are trying to learn a lot more about it or are in various parts of their quantum journey. What's that like too?
Yeah, absolutely. So my journey begins, well, back in high school, actually, when I read a pop science book about quantum computing, and I was just totally entranced. But then I went to undergrad and was able to do research in quantum computing at Berkeley, both in superconducting qubits in Irfan Siddiqui's lab, and then in theoretical quantum chemistry in Brigitte Whaley's lab. And so I got a pretty cool mix of theory and experiment in my undergrad research. And then I joined a quantum computing startup doing fault tolerance research in quantum architecture for about 3 years. And then I moved to Amazon in January of this year. Really kind of was curious to try out a different aspect of the field. I had been doing research for, at that point, about 5 years or so. And so it was kind of interesting to get a different perspective on what it actually looks like to think about what customers in this field will eventually be, or current users of Bracket, and trying to understand what they need or want in a service, and kind of more broadly where the industry is going as a whole, and having higher levels of strategic planning. And so it's kind of a variety of things, but yeah, that's kind of how I would summarize it.
Cool. Very awesome. And I think it's super cool that you actually got to work at so many of the awesome labs at Berkeley. Also, we have a question from Dario from Philippines. Is it advisable to attempt simulating qubits in multi-GPU PCs?
You can, sure. You won't necessarily get that much of a bump from doing that unless your simulators have been designed specifically to run in an optimized way on a GPU. I believe qQuantum has simulators that are designed that way, but it's not necessarily a sort of plug and play solution.
Sure. Is there any like intention to add qQuantum on some of your like EC2 images, for example, or is that like something you guys have in mind?
I'm not sure, but if that is a thing that's desired, we can certainly look into it.
We also have one more question from, what is your favorite topic in quantum computing?
Ooh, good question. My favorite topic is probably black holes and quantum information theory, kind of the intersection of those two, because you just end up finding out these really fascinating facts about weird correspondences that you would never expect, like the surface of a black hole, because essentially it bends space-time so hard, nothing can get out of it, like light can't get out of it, so it's black. But you can actually mathematically describe the surface of that black hole in terms of a quantum error correction code, which is just crazy to me. Like those things seem so disconnected, and yet it's like you can perfectly describe it with the quantum error correction. So I just find that there are so many areas of quantum information theory and kind of condensed matter physics that end up being just surprisingly connected, in that you can use exactly the same mathematical language to describe very, very disparate things.
I love the passion that you kind of gave off of it. I think that's what when you talk to people who are into like the quantum computing, they're like, wow, I want to do it because of some kind of like understanding that they have or some desire to understand through about physics. I think it's like one of those really amazing, awesome things that kind of inspire me day to day. So thank you so much for that. And I also have another question from Amir Raleigh, who asks, would it be possible to get in touch with you about any questions?
Sure, I will. I think I can post a link in the chat. I'll post my LinkedIn profile. You're welcome to reach out to me there. Or for the Twitter folks, I can also post that. They also have a Twitter.
Do you find that there's a stronger Twitter or a LinkedIn contingency in the quantum field per se?
That's a fair question. So I think most of the academics are on Twitter. Yeah, I think that's where the vast majority of professors, if you're on social media and you're like a professor of quantum computing or related fields, you're probably on Twitter. Yeah, LinkedIn tends, I think, to be more geared towards industry. Yeah.
Cool. And Nasser from Algeria also asked, speaking of black holes, do you see Amazon contributing to the study of ER equals EPR in the long term?
Only if it would be in service of building a product that customers really wanted. Amazon is not really the type of, it doesn't tend to do sort of pure research for its own sake, like a place like Google would. Amazon as a whole really tries to work backwards from customer problem, and then whatever you need to build is what ensues after that. So they definitely do have basic research that they do. So Amazon Science has a lot of really fantastic and like brilliant researchers. And obviously, if you're doing something like quantum computing, there's a ton of basic research that goes into that. And so we have plenty of people, say at the Center for Quantum Computing down in Caltech, where we're building our own quantum computer, who are doing very deep theory work, but it is in service of trying to build a quantum computer, which as a strategic goal is a very potentially world-changing application for a lot of different customers. So I don't know, maybe if it ended up being kind of, if it happened to be part of building a product, then sure, but I'm not sure if it would.
Yeah, I think it might take a little bit longer, maybe much after quantum computing is like a fully, AWS cloud kind of service with tons and tons of features. Then maybe, I don't know, and maybe we'll have like a feature as well where you can add it to AWS cloud. I don't really know, but that would be really cool on our side. So yeah, I think we're going to now just transition off to our next speaker. If everyone could kind of give a virtual round of applause, as well as a thank you to Jordan for coming in and speaking for HAQS. And please do ask any questions with regards to using Brocket in the Amazon office hours, which we will have someone from Amazon just answer any questions you guys have during the next 2 weeks. Thank you so much.
Thank you, everyone. Bye.
Next up, we are running a little early on schedule, which is great. Let your teammates know this is going to be a challenge reveal, and I think we had a question about what the structure for the challenges would be, so I'll just kind of take up some information and time here. So the challenges are provided are one with qSTEAM, which is the Quantum Undergraduate Science, Technology, Engineering, Art, and Mathematics organization that's NSF funded and led by Bennett, who will be speaking next. So this group is doing a awesome challenge on entanglement, which they'll release. Secondly, we have the QSF October monthly challenges. Those will keep you eligible. Those are the October monthly challenges, which Alberto from QSF will be speaking about. And then we have our very own, which will be a VQC challenge, as well as the open-ended qBraid SDK challenge. So there's a total of 4 challenges, and you'll be eligible for prizes for all of them. And what's great is for the VQC challenge, we want you to essentially run a model and then upload your, and you'll essentially just make a PR request and we'll check it, make sure that your accuracy is validated, then you'll be updated on the leaderboard. So stay tuned for a little bit more on that. And without further ado, I'd love to introduce Bennett here from qSteam. I'm going to make sure he's pinned.
Yeah.
Hello, good morning, everybody.
Hello, hello. One more second as I figure out how to pin.
Ricky, you
There
want?
we go. All right, spotlight. And without further ado, I'd like to introduce Bennett Brown, Executive Director of qSteam, a nonprofit membership network of colleges, universities, employers, a lifelong champion of equity and access to technology and education.
Thank you.
Brown, yep.
Great. Thanks, Ricky. Hey, thanks everybody for being here. This is really exciting. I am executive director of an organization that was just incorporated last week, a week ago today. We've been working for a year under NSF Convergence Accelerator support. We are 75 professors across 25 different institutions. And I was given the job of scaling that effort to include hopefully 300 colleges and universities within 4 years. So the idea is to take what we've learned and spread it to other campuses. We'll begin that in the summer, where we'll have workshops for each of our courses. So our vision here, I'm just going to talk briefly to you about why qSteam is providing this problem. So our vision is that quantum information should be accessible to everyone as a learner. And yet we know that it's interdisciplinary and requires background knowledge that really even professors are uncomfortable teaching the courses sometimes, because they may know a lot about physics, but not much about computer science. So it's difficult for institutions to stand up quantum information courses, and we may aim to make that easy by providing professional development, curriculum that is modular and customizable, as well as connections to industry, so that their students have somewhere to go once they've completed the coursework that is offered. Perhaps just a little bit of coursework on a campus, or maybe the campus offers all 8 of the courses that we're developing. We currently have 4 courses in pilot across our network of 25 universities. And we really try to solve 3 problems at once. So we're trying to address the diversity of campuses and people that feed the workforce. We're trying to address STEM pedagogy. Let's make this an effective learning environment. So if this were a normal classroom, I would right now, within the first few minutes, ask for participation. You can do that in the qSteam Challenge channel of Discord. Introduce yourself if you plan to work on our challenge. And instead of stopping there, I'm just going to proceed here. So we have a lot of different universities, from the big R1s to we have North Carolina A&T is a research university and a historically Black college and university. We have a dozen HBCUs, a couple community colleges that are piloting our courses. So we offer quite a range of services, both at the academic side to support universities and colleges standing up coursework, as well as to industry. So we try to give students an opportunity to connect to industry, and industry an opportunity to connect early to students, so that they can turn that into an employee-employer relationship. Or a co-founder relationship. This is a list of the courses we're offering. What I'm about to share with you as the challenge, or what the qBraid folks will share by making that repo public, is I'm not going to say it's excerpted from our course 2, in which students use qBraid to program real quantum machines and measure results. It's a little bit of a mix, because our first course is intended as a general education course, or as a 0 level course for STEM majors. Computer Science 0, for instance, has become popular across a lot of campuses and has drawn in a tremendous number of new people into computer science. So our first course in some ways is a QISE 0 course and a QISE 1 course. People are using that in both implementations. The QISE 2 course is really at the heart of what you're going to be doing if you're participating in our challenge. Teams of 2 to 5 can create entanglement. This is the reveal. Is it too early? I better stop there. Okay.
Nope, you're good.
Okay. So you're going to create some entanglement, do something, in fact, do 2 different things, and then measure the entanglement. That is an example of a QSTEAM problem that has ground level entry. In this half hour, I can show you, you've already been shown this morning how to create entanglement and then measure it. But the measurement of entanglement is an open research question. I can show you one way to calculate it for a 2-qubit system, but as soon as you get to 3 qubits, there are already 2 known or more known ways to calculate entanglement. And what that really means is a bit open, and perhaps there are more methods. So we're asking you to generate an experiment, to perform an experiment and then explain it to the layperson. We've articulated specifically what the layperson can be assumed to know. These are students who are marginally ready for calculus. So that's your presumed audience to explain your experiment and the results of your experiment. Rather than a competitive hackathon problem, this one is more like the QSTEAM curriculum, where we're really not trying to create a competition among students. This should be a collaboration, to use the words of Woody Flowers from a different competition here in robotics. So the certification by the panel is that you have produced evidence that you understand entanglement. We provide professional development to instructors and an industry engagement, and that's all I'm going to show from that deck. I want to show you the challenge here. So you'll be forking this repo, and I put 2 files in there, a README that describes the challenge and a version of the starter code that was provided already from Kanav. So here's a little bit about us. And then the hackathon challenge. Always in education, you want to provide the goals front and center, and then throughout the learning experience, understand how well you're doing against those goals. So we'll have opportunities for feedback for intermediate results here, and opportunity for you to give feedback to other teams. We'll clarify that more later in the challenge. But the goals here are to construct a circuit, investigate entanglement, and do that again under different conditions to design an experiment so that you have an independent variable where you're doing 2 different things that might generate noise. And then at a level of beginners, explain your results. So the preparation of an entangled state and measurement of results, here are 3 examples. You might prepare simply a Bell state. That's an entangled state of 2 qubits. It's actually maximally entangled. And then you could wait a while and measure, well, how entangled is it now? Does the 2 qubit state lose the entanglement over time? That could be your independent variable. Your independent variable could be, instead of changing the time, keep the time constant, or at least, you might use different Python modules to assure that to varying extents to control that time variable. But the idea here is really to explore at first before you try to create publishable results. And you could take a 3rd qubit and flip it back and forth between eigenstates in the Z direction, the 1 state and the 0 state, and then measure the entanglement on the first 2 qubits that were in a Bell state and see whether the 3rd qubit changes. What you do on the 3rd qubit changes the results that you end up measuring on the first 2 qubits. The 3rd example here in this 3rd bullet, to prepare a Bell state on various distinct pairs of qubits on a particular platform. You could prepare the Bell state on qubits that have a better connection to each other than that have less noise that would interfere. You'll have to investigate what exactly that means. So there are a lot of different things. These are just some suggestions, and I'll show you briefly how you could calculate a measure of entanglement, but I want to note again that this is an area of ongoing study, and you can use any method, including one that you make up, as long as you use it with explanation. You might refer to this article, Entanglement of Formation of an Arbitrary State of 2 Qubits from 1998. I'll show you a method you could use. The thing that you're submitting for the competition, I'm going to take a second and see if, before I proceed to this, are there any questions? You can ask them here in the Discord. I'll try to keep an eye on that throughout the time here. I see that we have, there's the reveal. Thanks for the reactions to these 4 people. So you can ask questions starting now in the qSTEAM Challenge channel of the Discord. Coming back to the deliverable, you're going to create a Jupyter notebook that, again, to scroll up here, you're in that Jupyter notebook, you're providing both code and explanation. You're linking to, this is, I haven't mentioned this, you're linking to a video or embedding the video in the Jupyter notebook. Can't be more than 5 minutes, please, and include a transcription of your audio. And in that video, you're trying to summarize your experiment and results, especially where you have more space in the Jupyter notebook. Aim for the particular audience, but also in the video. So that Jupyter notebook should include written explanation in English and math that a first-year college student marginally prepared for calculus will understand: claims, evidence, and reasoning. Those are 3 terms that ought to be ground into the heads of US high school students from the next-gen science standards. So the specifics of what that means are below in the rubric. You should also provide your code so that it will execute on a simulator backend, and so that it executes on 1 or more physical backends. If the physical backend is your independent variable, of course, you'll want to be on more than 1. And if it's not your independent variable, pick 1. The background knowledge you're allowed to assume, as long as you remind the student in your video or Jupyter notebook, is listed here. So exposure, these are things that the students ought to have learned previously in the course. This is essentially where students are partway through course 2 in our materials, and just sort of at the beginning of course 3, where we're reminding them of how to do these things or what these things mean. The conceptual stuff, like this, identifying the results of the 2-slit experiment, repeated Stern-Gerlach measurements, as long as you're making them in the measurements in perpendicular directions for the beam splitting, and delayed choice experiments are in our first course at a conceptual level, where we try to delay the math rather than make the explanations of the concepts dependent on the math. It's concepts first in course 1, as well as in the other courses. So you can assume that students are familiar with a variety of notations, and that they know how to write a bit of code to create a circuit that's simple. You can assume that they know some of the math notation, but not all of it. So if you're going to explain that an entangled state is something that you can't write as an inner product, then you have a lot of explaining to do. And that's the challenge that the professors as curriculum writers faced. So we wish you luck with this challenge. We hope that you will be an example of the qSTEAM model, where a large community of instructors and learners can improve the materials that are available and share them with each other and build and riff on each other's work. There are certain things that we want you to assume without having to remind students of anything, and so they're listed here. That's basically a pre-calculus level of mathematics, and your submission will be based on these 4 criteria evaluated by a panel to say, did the team produce evidence of understanding of the 4 learning objectives that I showed above. I can answer questions about qSTEAM, I can answer questions about the challenge, and I can also give a little bit of instruction for those of you who are beginners. So I want to point out that many of you, I hope, might be a little fuzzy on some of this. I hope that we reached an audience of people that are genuinely new to quantum information. And so your learning journey might include reviewing some of this content and will be available to help you with questions on that throughout the challenge. You can ask questions in the Discord, and we'll also have some live sessions. So let's see, this is a nice tool for describing. Let me see if there are questions, and then if not, I'll instruct just a brief while here. No questions here in the qSteam Challenge channel. So I'm going to go ahead and share with you some of the basics. If I get something wrong, feel free to say so in the qSteam Challenge Discord. I myself am I'm not going to say I'm new to quantum information, but I am not a professor. My degrees are in physics, and I did do work in quantum, but not in quantum information. In 2013, I printed out this article, realizing that it changed everything about observing single quantum trajectories of a superconducting quantum bit. Wow, that is the time that I became aware of quantum information. And I'm excited to work with this diverse group of professors from physics, electrical engineering, computer science. We're from 15 different departments: biology, philosophy, and the fine arts. So the circuit that I'm showing you is the simplest way to create a Bell state. This is a tool from a Google engineer called Quirk. And I could put that in fact, why don't I do that here? I'll just share with you. This is a way to explore. You don't have to limit your work from, thank you for that question. Here's this is a nice tool for exploring a circuit. And there's a question in the chat. Can you give us the link to the paper? Absolutely, though this is just the link to the abstract. I didn't want to violate the author's intellectual property rights. So I didn't share the whole article, but feel free to use your institution's credentials to get that full article. So this is, each line here represents a qubit in this circuit. And this is actually not the one I was just showing you, I think. There we go. So each line is a qubit. And on the left, the qubits are initialized to the 0 state, or the lower energy state in some two-state physical system. This is just a simulator, so there is no physical system. This is a Hadamard gate, which I've dragged onto the circuit from the palette above. Now there are two Hadamard gates, and I'll leave that there for a moment and return to remove it by dragging it off of the circuit. This is a condition. This black dot means only do the action down here, which is an X gate or a NOT gate. It revolves on the block sphere, the representation around the X axis. So this is a C NOT gate. It's a conditional NOT gate. And what this one does right now, it's this qubit is initialized to 0. A Hadamard gate is its own inverse. So Hadamard returns the qubit to the 0 state. And I can visualize that with one of these 4 displays. If I drag the block sphere on here, for instance, I notice that the state is at the top of the block sphere in the 0 ket, in the Z basis, in the calculation basis. And if I look at what that qubit was after one Hadamard gate, which is how I'm going to leave it. I'm going to get rid of this Hadamard gate. Well, I'll leave it on for a second. So a single Hadamard gate revolved this state on the block sphere around the line X equals Z, which the tip of the finger, if you can see my mouse icon on Zoom, is pointing to that, a point on that line. And so revolving the 0 state in a cone around the X equals Z line landed me in this state. You can actually get the Bell states, which are maximally entangled states. So this is now resulting in 2 qubits that are not in a single qubit state. You cannot any longer describe this qubit on its own. The only way to describe this top qubit, the 1's place qubit, if you will, and then this is the 2's place qubit. And if I had an additional qubit, now this is the 4's place qubit. And when you measure them at the end of the circuit, you could measure all the qubits. You can also measure before the end of the circuit and turn that into a classical bit. You can also do what's called a post-select, where you measure it. And from that point on, you're only looking at the groups of measurements that would happen on the group of qubits where you measured a 0 on the ones place qubit. That's called a post-select. So going back to, well, here's a circuit. Why not leave the Z gate on there? When I measure all three, so this is a rotation around the Z axis. It did nothing to the initial state. This qubit is not entangled with the other 2 qubits, and that's why the block sphere has a representation of that qubit. When I measure these 3 qubits together, I might get 0, 0, 0, which is represented here. The 0, 0, 0 in binary is simply 0, and in that green box you see decimal 0. So this is the 0 state, the 1 state, the 2, 3, 4, 5, 6, and 7 state. And you can see from the, if you think about sort of like these figures here are showing the chance of measuring a 1 on that qubit. So if it were all green, that'd be 100% chance of measuring a 1. If it is no green, it's 0% chance of measuring a 1 on that qubit. And these blue bars in the background behind the circles in a visualization like this are showing the probability of measuring here 50% that I would measure 0 and 50% that I would measure 3. The 3 is represented as 0, 1, 1, and you can tell that from the row and column headers on the right and bottom of this little outcomes figure. One thing that sometimes confuses students is that they'll view, if I want to look, that's called an amplitude display. And if you look at it on 2 qubits, sometimes people will confuse that with a density matrix, which might be new to you. That's not correct. The density matrix for 2 qubits is going to be a 4x4 matrix. And the diagonals of the density matrix are reflected in this amplitude. So this box corresponds to this upper left box of the density matrix, and all of these boxes correspond to the diagonal of a density matrix. So if I show a density matrix across those 3 qubits, that's going to be 8 by 8. The diagonals indicate the probability that I will measure 0, 1, 2, and 3, and so on. So this state is 50% likely to be measured 0 and 50% likely to be measured 1. Let me check what I'm doing on time. Great, I have 11 minutes, and I'm going to shift. I'm going to stop. Have I been screen sharing? I don't see the green boundary.
Yes, you have been.
Phew. Okay, so I'm going to stop sharing and shift my camera. If you'll look at the pinned camera there, I might go through and iterate. Good, I went straight to my whiteboard. This is a way to describe, another way to describe a 2 qubit state. So this is the complex amplitude of the 0 state, 0, 0, 0, 1, 1, 0, and 1, 1. And the circuit that I've been showing you, a Hadamard followed by a C0, creates a Bell state if the qubits are initialized to any Z eigenstate. So if I initialize the qubits to 0, 0, I start with the 0 on this qubit and 0 on this qubit, and I do a Hadamard on the first qubit and a C0 across the 2 qubits, then my result here is in the Bell state. That's going to be 1 over root 2 that I measure it in the 0 state of the 2 qubits, and 1 over root 2 that I observe them both in the 1 state. That is a 100% correlation. I only need to measure 1 of the qubits to know what state the other qubit is in. And if I send that other qubit to a remote location, then that's spooky action at a distance, verified by measuring Bell's inequality and CHSH experiments. So I want to point out that our problem is not asking you to prove that they're entangled. They might simply be correlated. And if you were to demonstrate entanglement, that would be impressive, but you can explain the entanglement. And you certainly could demonstrate entanglement. So on the same machine, you're going to measure both qubits to be 0 or both qubits to be 1 if they are in the Bell state. But when you actually do that, here I'll show on screen share in a Jupyter notebook, that you're going to measure some noise affecting the system and causing a transition from the 0 state or the 3 state, where all of the measurements ought to, you ought to measure that state in one of these 2 states all the time. But in fact, there's a transition from that builds up amplitude in the other 2 states. You can calculate the amount of entanglement. And if I've lulled you to sleep here, this is the key point. So one way to measure entanglement is the product of these 2 amplitudes minus the product of these 2 amplitudes. That it's AD minus BC gives you one measure for entanglement. And you can prove that that number is always has a magnitude between -1/2 and 1/2, and that these represent maximally entangled states, that the 4 Bell states are included. This Bell state that I've written here is the plus state, denoted as, let's see, I might get this wrong. Is that psi or phi? I believe that's going to be phi plus. I'm pretty sure of it. So that's that Bell state. I need a little equal sign in there. I'm sure that many of you here in the audience have expertise of a quantum engineer working in the field. So the challenge for you will be more how to explain this to a beginner. Others of you are new at this, and you kind of have a leg up here, because no matter what you do to explain it, you're going to be explaining it at the level of a beginner. And if you get some technical details wrong, then that's your challenge, right? Is to make it technically correct and accessible. All right, so in the last minute here that I have, let's see, I'm at 12:53, 7 minutes. I'm going to go back to screen share. Let me check for questions about what I've just said. So screen share. Uh-oh, my Zoom interface disappeared altogether. There it is, it's hidden behind the chat. That's strange. Okay, so go back. Screen share. Here we go. All right, so let's see what you've had to say about the qSteam challenge. What is the audience of Quirk? That's a good question. I don't know why. I want to give him credit. So I'm going to demonstrate, he was publishing a weekly blog for a long time. I thought it had his name right up at the top. If somebody knows it, you could put it publicly in the Zoom chat. That would be great. What was his, I think it was himself, actually. I think that he was trying, lots of people use that tool. It can be a beginner. Certainly this tool, I mean, look at it. It's like such a crowded interface, and it would be great to have a little lever on the side that let you start as a beginner. So I don't think it's intended for beginners, but I find it very useful for teaching beginners because you can get into the notation. If you're interested in using this interface, I'll point out that you can click on the initial state and choose something that's on the positive or negative axis of any state on the block sphere. So what I'm doing here is cycling through the 6 orthonormal states of the different bases of the standard bases. Okay, so let me shift now to show you the Jupyter notebook that I've shared with you. So this is really just a reduction of the Jupyter notebook that Kanav and team have shared with you about getting started. I just didn't want you to have to sort of go to 2 places. So the way these Jupyter notebooks work, all the text is actually, like, if I double click on this, I'm editing Markdown, and you can execute those cells again with a Shift Enter. So I can just press Shift Enter and kind of work down my notebook. This is commented out, and you're going to want to delete the comment and execute it for yourself. I think if I do this, it's going to say it's already enabled. Let's see. In the brackets, you'll see, I think that doesn't show a star because it's a shell escape rather than executing in the Python environment. So, and I don't actually want to re-execute this because it takes so long to import all those files. I'm going to skip it and just start again, enter, shift, enter, shift, enter, shift, enter, and so on. So at that point now, you'll notice, oh, up here it says no kernel. So I need to restart my kernel. I want to make sure I'm using the bracket kernel. I'm going to select that. And that's probably why I wasn't getting a message here. There we go. So I've already enabled qBraid. I'm going to skip this one. Well, if I restarted my kernel, I'm going to have to do that. And that's going to take a little bit. It'll stay in asterisk. I can execute other executable cells. So you can look at these cells to find out, like, well, how did they make such nice notation? You can just double click to see that. So $$ is a way to use LaTeX, and you can write a fraction, for instance. So your job is to create a Jupyter notebook that teaches people about your experiment. Shift enter so that it renders that. Shift enter. So let's see, it's finished importing them. And now I'm going to go ahead and create a new circuit. If you're new to programming, I'll give you a hint. This is object-oriented programming. The capital C is an indication to you that you're creating a new object, and things that come after the period will do things to the object or access values of the object. This is called a method of the object. It's adding a Hadamard gate on the 0th qubit. This is adding a CNOT gate to the result produced by the code before the dot. So that's producing the circuit above. Again, you can just remind people of this. This has been shown earlier in the course, but it's always a good idea to repeat the fundamentals. This is printing the circuit from the AWS library. I'm creating a device. So here I need to go back, shift enter, shift enter, shift enter. Shift enter will execute this because this is code rather than markdown. And I've now created a device that is a local simulator. And now I'm executing the run command on the device. That's going to return something that has a result method, and I'm storing the output of that method, the return value, in a variable called result. And then I'm accessing a variable that is part of that object and putting it into another variable, counts, and then I'm printing counts. This is telling me that I got the 1-1 result 507 times and the 0-0 result 493 times. You might find, if you refresh your quantum jobs over here, that it still says initializing. This is indicating the status at the last time in which you use the Jupyter Notebook to check the status. So to update this, that refreshing here will show new jobs, but it won't show a fresh status. To do that, you need to, and I'm telling this because it's a stumbling block that is common. So if you copy the job ID and use that, there's some code at the very bottom for task recovery. You can paste that job ID right into that task. I think I just pasted without erasing the E, so I'm going to delete that one character and shift enter to try to get a result from this Oxford computer, and it is still queued. And now this will show, if I refresh, this will show the current status. That's what I got for you. I think I'm right on time at 1 o'clock. So good luck to you. I'll try to make myself regularly available to especially the beginners during these 2 weeks. And I wish you good luck, and hope that all of you that participate get the certification that as a team, you have produced evidence of understanding of stated objectives. So once again, those objectives are stated in the IPython repository, and it's my hope that you will learn how to construct a quantum circuit to entangle qubits, to investigate entanglement, to design an experiment, and to explain the results. Good luck, everybody, and thanks for your attention.
Thank you so much, Bennett. That was a wonderful talk. And if you're getting started in quantum, I think this is an excellent challenge to get started in. And I think what's wonderful is that, we have challenges at every level. Alberto next will be just speaking about the QOSF challenge, which will be about the regards to the October monthly challenge, which will get you qualified to be considered to a mentorship program through QOSF. So without further ado, I think we do have a few questions.
Oh, I'm so sorry. I forgot to leave 5 minutes for questions.
No worries, no worries. So thank you so much for the awesome talk. And we have one question, I think, here. Let me pull it up. Yes, isn't AD minus BC, so the determinant, if it was a 2x2 matrix instead of a 4x1. I think this is regards to your Quarks demo, and this is Dario from Philly.
Yeah, if you had a matrix that contained the four elements A, B, C, D, sort of reading left to right, top to bottom, the determinant of that would also be AD minus BC. However, the density matrix, a square matrix representing this 2-qubit state would be 4x4. And so that's not the determinant of the density matrix. It's also not the determinant of the 1x4 vector that represents the state. So that's why on the whiteboard, I explicitly wrote the 1x4 matrix and said it was equal to the sum of 4 kets that had amplitudes A, B, C, and D, and that the entanglement would be AD minus BC. Good question. Thank you.
Awesome. I think we might have 1 or 2 more questions, and then we will then move forward with Alberto. And then just to get started.
Thank you so much, Ricky.
Yep, I think we're good. So let me turn off the spotlight and make you a spotlight, Alberto. So you're ready to go. This is once more another challenge reveal. So we have a challenge presented by Alberto.
Okay.
And Alberto, I'm just going to give you a quick bio read here. Alberto is a PhD student in computer science at the Institute Politécnico Nacional de Mexico, where he is doing research on quantum machine learning. He collaborates with Fermilab on error mitigation and won the qC-HAQ 2021 category and 3 qC-HAQ 2022 categories. Alongside that, he is not only in Peak, he has an internship at Entropical Labs supporting the Open QAOA SDK, and is a QSK advocate, Quantum Open Source Foundation, and a volunteer at IEEE Quantum Education. Not only that, but he is super excited to also be a community manager at qBraid. So glad to see him, and definitely join Quantum Universal Education. It's a great group just to learn more about quantum, and it's a really great community as well.
Thank you so much, Ricky, for the introduction. Well, in this case, I will talk about Quantum Open Source Foundation and the reason we're here. Well, in this case, we are talking about for the challenge and the mentorship program for Quantum Open Source Foundation. Originally, this program, it was idea for, well, it's for Quantum Open Source Foundation, a non-profit community interested in share different knowledges, research, frameworks, different technologies about quantum computing in general. So in this case, we had a specific part, the mentorship program. In this, the idea it was a connect with the global community about quantum computing and try to help person who has beginner or interested to do a career in quantum computing. So in this case, you can participate in an individual way or in a team of up to 3 members. What is the reason for this? Well, we had a different cohort, 2 for each year, and that is try to motivate different people who has interest in design different materials. It could be educational materials at the intermediate level. There are many blind alleys that one can get into watch meal severely slow down their progress. It's easy to get a distorted view of the field from the outside. So the reason in this case is we can connect with people with background like computer science, physics, chemistry, economics, biology, and other you have interest in connect with quantum computing and try to motivate them to understand different areas using this technology. And what is the necessary thing we can use in quantum computing or in this mentorship program is knowledge of quantum computing and the basis. It could be if you had knowledge about by books, by your course, by your PhD or master's degree, it could be help you to participate in this case. If you are helped with the coding skills, it's very important. So in this case, we designed a mentorship, a monthly challenge. In this case, we designed different problems using different frameworks, and you can try to solve it and motivate what's the project you can design in this mentorship program. And finally, the motivation is you can participate with experts in the industry on the academic part. Like in the right part, you can see a lot of names who has participated like a mentors in the previous cohort. So the reason for this is you can participate with an expert. They can help you with different ideas, and you can participate to improve your knowledge, your skills, your coding skills, like like an internship. Well, we don't save any money, but you can improve your knowledge with amazing and interesting persons in this area. But for this part, we had a problem. Sometimes you are more a theoretical part, or you know basic frameworks or basic knowledge about the framework. So we designed different challenges, the monthly challenge. In 2020, we started with the science different challenge for different topics like quantum machine learning, quantum algorithms, quantum imaging processing, quantum cryptography, and we can, oh, quantum chemistry and optimization. So the idea is you can starting with one basic problem and you can design the different methods. It's not necessarily one specific. And the benefit is you can use any framework. It could be even using only NumPy. You are good in this area. So you can improve your code and you can understand the basic idea and you can propose a solution. If the solution is correct, for this, you can do a pull request with your proposal solution, with your username, and you can do a contribution in this repository GitHub. So the idea is you can participate with different knowledges and you can improve your your skills, your code skills, and in a specific and multiple specific problems. That it was about general stuff in quantum computing, or you can work with quantum algorithms using like passive learning algorithms, just algorithms, Grover algorithms, or quantum compute or quantum machine learning. So the idea is you can participate in different tomography. So the idea is you can participate with different knowledges using quantum computing and time to improve. For what? You can participate in the mentorship program. In the mentorship program, we design 4 tasks. Each task is for different area, and the proposal idea is you can participate in this one and try to solve with your knowledges. We can consider a specific problem, and you can obtain a bonus. Depends on your coding skills, your foreign document this or explain your proposal solution, and the the technical how you can understand the problem and how you can improve the idea. It's not necessarily only solves the basic thing. You can try to improve more for explaining, for understand the idea and how you can code clean these kind of problems. And that was considered for the mentorship program. In the mentorship program, one mentor can select your project. He evaluate, he puts certain points, and depends on the points, the other mentors or the same mentor, it could be considered you for the problem. For what? For someone solves a problem. That it could be a open source problem for a specific framework like Penelens, Orchestra for Zapata Computing, or Tequila for another framework. So the idea is you can improve one open source project or a research project, because that is the reason for this mentorship is improve your skills and help you, depends of the area for the mentor, helps and improves your skills in quantum computing. And in this case, this is the last cohort, the cohort for the October, and this is the problem for them for this challenge. And the idea is you can participate with the task number 1 is a multiplier. You can consider different ways to design the design the addition solution with 2 integers values or numbers and try to implement a quantum computer. And using this one, you can design a multiplier with 2 integer numbers. That is, you can improve in a general number, not necessarily one specific. For example, 5 and 6 is equal to 30, but you can use for any number and binary and check what is the capacity for the framework or for your computer and simulate this kind of solution. The second one is the size a missing number. Is in this case is you had a vector with the size 2 to the n minus 1, and this has a no order in the vector. It could be 0, 3, 0, and 1, but we need to check the order or what is the number we can skip. In this case, it's the number 2. So you design an oracle. It could be one hint. It could be using global algorithms and trying to check or Basirani algorithm, and to identify with any vector with size 2 to the n minus 1 what is the missing number in this case. Depends of this, you can identify what is the best combination or what is the maximum number of the vector, what is the time you necessary to understand this, well, obtain the solution. I understand your explanation or motivation for what is the reason or the way, what is the correct way to solve this problem. It could be that one, or it could be, I don't know, we can say QAOA, that is a good implementation or no, or using variational quantum circuits is okay in this kind of problem. Your solution, try to motivate you understand what is the benefit or what is the best case using certain specific algorithms for specific problems. The other is using more in the quantum computing area is Motonen state preparation. In this case, you are preparing for data set, this encoding part, in preparation for the encoding states. In this case, is use a vector for 8 elements. And you understand a specific problem using any framework. It could be a cascade serial panel line, Amazon bracket, everyone you have interested in this case. And the previous one is the same. The idea is you understand how you can implement this for any vector, but we can limit it only for 8. You can prepare it other size and trying to prove what is the limitation considers the number of the qubits, the number of the gates, the depth, and put a criteria what is the benefit of the limitation in this kind of applications. And this task number 4 is identifiers. We are considered the BB84 protocol to generate a key. And in this case, you are using the teleportation algorithm for send the image. In this case, the image is the Quantum Open Source Foundation logos for one folder to another folder. It could be, in this case, is a local computer, not necessarily in 2 different computers. Well, in this case, how you can implement this area? What is the benefits of the limitation using the cryptography in quantum computer and send the files all the initially part for the protocol in quantum internet. You can use in the same line in the previous one, different frameworks, different possibilities, and try to see what is the benefits, the limitation for your quantum computer or the simulation in this case, or your computer specific, and what is necessary for this kind of projects, or what is the importance to solve this for the mentorship program is because we need to understand who was the person indicate or prepare it using this kind of projects and understand the idea because the mentors are necessary to understand how you can think in quantum computing problems. Is the multiplier is understand the basis for quantum gates, like similar with missing number, but in this case, how you can implement the popular quantum algorithms like Grover, Deutsch, and Bernstein-Basirani. The third one is how you can prepare in different quantum gates. Not necessarily this is for quantum machine learning. Well, it's a state preparation has popular in quantum machine learning, but it's important how you can understand the idea how you can encode in classical data in a quantum state because that is a not simple 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 problem. So the idea is we can understand different problems with different areas, and depends on your interest in, we can understand your knowledges, we can understand your skills, and we can decide if you are the person to match with the projects for the mentors. And the last one is the same, how you can implement projects like in the industry or for the open source projects. So in this case, we are designing these projects, and we can help. Well, we are interested to help you and improve your skills. And necessarily in the mentorship program, you can work. I think in qBraid now has in the platform. You can select the mentorship programs, and you can improve that to do a solution. The idea is if you not select in this cohort, you can participate in the next one. You can improve your skills, and this is like a guide to help you to improve the quantum computer algorithms projects if you are interested in a research area or in the software developer things. And yeah, like say Ricky, if you participate in this and if you win, we can consider for this 6 cohort in the mentorship program. And thanks, Ricky. I think it's all for my side.
Great. Thank you so much, Alberto. That's fantastic. Just want to clarify, this will be for cohort 7. I think cohort 6 is going to be decided in on the 28th of this month. And then so this is really fantastic. It's a great intermediate challenge that people can kind of ask any questions in the QSF challenge section. And again, these will cover kind of basic algorithms such as Grover's. And what is also great is, I think Rishabh Singh is asking if you can use any SDK such as PennyLane, qBraid, or Bucket. Is that correct, Alberto?
Yes, you can consider any framework. And it doesn't matter. The important is how you can solve the task. That is the specific problem.
Great. Yes. So for those who are using, the QSF challenge, it's open source. That's a great part about it. So you can use whatever you feel comfortable with, and you can use it on qBraid. And what would be even cool is maybe if you even add like the qBraid SDK component to it as well to qualify for the qBraid SDK Open Challenge, for example. That is something that we'll be talking about shortly.
Yes, exactly. The idea is you can solve the project, but not necessarily for solve is correct. You need to explain. You need to give a reason what is the reason your proposal solution is the correct and not the other one. You need to limit it. You can explain the different problems that you can consider like correct, but you give us a reason in your explanation. Depends of the papers, depends of the previous cohort. What is the reason you can consider your solution is good? Depends of the limitation, depends of the problems. That is the benefit we need to understand for you in this kind of challenge.
Great. We also have another question from Harold Kimmy. Is it okay to use TensorFlow Quantum and a generative machine learning algorithm to figure out the multiplier missing value?
For this challenge, not, but in the previous cohort, we had like machine learning. Let me say let me a moment. This one. Yeah, you can participate. Yeah, sometimes we have one problem for quantum machine learning problem. One problem it was this one. We get you two specific data set. And depends of this, the problem it was how you can encode these mock data sets in a quantum circuit, variational quantum circuit, and obtain a good performance. Good performance is could be better than 85%. That was the consideration. So in this case, we need to identify a binary classification, and you can consider in this case is okay. You can consider any ansatz for classification, but what is the encoding? The encoding not necessarily it could be rotation. Well, it could be rotation in X, Y, and Z, or you can consider the amplitude encoding, Bayesian encoding, a combination of this one, or a specific kernel you can find in the different frameworks. Well, that data analyst consider the distribution of the data. That could be a key to solve this problem using a short number of the qubits, because it could be 2 qubits, 3 qubits, 4 qubits, 5 qubits, 10 qubits. So it depends of this kind of problems. You can limit it for the number of the qubits, number of the gates, and what is the benefit of this kind of problem is a great accuracy. So yeah, we are considered all the different areas in these monthly challenges and in the mentorship program.
Great. Awesome. So just want to also mention, Alberto, how did you kind of get started in quantum? What was like your adventure to it, and what makes you like really, what's like some kind of driver or motivator to keep you always like learning about it?
Okay, my motivation. Well, actually, I was studying in this area when I started my master's degree in quantum computing. Even in that moment, I don't have any idea what it was the bracket notation or what is even a qubit. So, and this motivated me more participate in this kind of events, the hackathons, the challenge, to improve my skills in the mentorship program. I think that is the most benefit I did. And I can help another person like in this kind of events, because you can start only reading the books or the tutorials, but that is a limitation. You only understand the basic stuff. But how you can apply this kind of knowledge in real programs, like that to solve the tic-tac-toe, for example? It could be common or simple in classical computing, but in quantum computing, how you can solve it? That always gives me a question. So this kind of events help you to understand different point of view and try to improve your skill. Actually, we designed the last Tuesday, if I'm not wrong, with Ryan, the CTO, a panel about open source and quantum computing. And the great thing it was all the person who has interest in this is they works in different academic or the industry or in the communities. They they see the necessary part is participate in open source projects because you can help other communities, you can win knowledges, improve your skills, and that is the reason I'm working with this with Quantum Open Source Project and Quantum Universal Education because you can share your knowledges, you can improve, and always think if you teach to another person your ideas, you can help two persons, you because yourself because you can improve how you can explain your ideas and to other person because you can motivate other person to connect with this area. So the other thing is if you teach you can learn more than only participate. That is another recommendation. So teaching, um, programming the different challenges that is help me too much to work in different projects in quantum computing.
Awesome. Thank you so much, Alberto. And thank you, QSF. And we have a question that's not related to QSF challenge by Amarelli, who's asking if the QVC challenge is available. And the QVC challenge, the quantum variation classifier, and the qBraid SDK challenges will be announced very shortly in our next session. And I think maybe we can just get started with it. I'm going to do a quick overview of our next speaker in around 7 minutes. And then we'll do a quick challenge reveal. But in the meantime, if anyone has any questions, please do mention in the talks chat. If you have any questions for Bennett, or if you have any questions for Alberto, please just mention it and feel free to keep asking. It's really wonderful when you do. And get started on these challenges on qBraid. So yeah, we'll get back to you guys in around 5 minutes. All right, everyone, this is the final and big challenge reveal. This is the qBraid-HAQS 2022 challenge reveal. We have our very own CTO, Ryan Hill from qBraid, and he holds a Master's of Engineering in Physics from Cornell University, where his research focused on QML, specifically on quantum neural networks. Yes, and more focused on that is he is an active member of the quantum open source community with code and community contributions to projects, including Penny Lane, Qiskit, Amazon Brocket, TensorFlow, Microsoft Quantum, and Quantum++. He's a quantum coding boss out here, and he's doing an amazing job with just like doing this challenge. So if you have any questions with regards to the challenge, do message him on Discord. And I'm going to stop sharing my video, going to pin Ryan. And without further ado, please take it away, Ryan. Thank you.
Thank you so much, Ricky. Hello, everyone. Super excited to be sharing these challenges with you and to be kicking off this HAQS event. I'm super excited about it, and I have super fun challenges here for you guys. So I'm going to go ahead and share my screen. Let's see. Sure. Okay, yeah, right over here. Okay, so I'm gonna start the slideshow. All right, so like I mentioned, my name is Ryan, and in this talk, I'm going to be mostly doing a challenge overview. I'm going to be going through both of qBraid's challenges that we offer, and I'm going to do that pretty briefly. I'm going to spend 10 minutes or so kind of going through the challenge repository and briefly overviewing both. Then I'm going to spend a little bit of time giving you some background on each of the challenges. So I'll do 15 minutes, giving a little bit of a VQC background. There we go. And then I'll do a qBraid SDK demo to kind of motivate that challenge. And then I'm going to leave a lot of time at the end for questions, because I think that'll be well used. Okay, so on qBraid, we are offering two challenges. The first is a QML classifier challenge. So in this challenge, you're going to be implementing a variational quantum classifier, otherwise known as a VQC, to solve a supervised learning problem. And then there's going to be an open challenge as well. So this is just going to judge the most creative or compelling use of the qBraid SDK. So I'm going to slide over the challenge repo real quick. HAQS 2022. Okay. So some of the past speakers have been over a little bit of the getting started directions and the launch on qBraid button. So follow these getting started instructions. I saw a question earlier about working in teams and how the forking works. Your group only has to create one fork, and all of your team members can work off of that fork. They just need the git clone URL for the fork. By forking the repo, it'll remain public as is intended. If you want to create your own private repo and push changes and then commit your changes to the public fork at the end before you submit, that's totally fine. There's a little YouTube video here giving a quick 2-minute demo going through all these instructions at once. So if you're having any problems, you can just follow that demo. And basically at the end of it, after you followed all these steps, I've provided a notebook, verify setup.ipynb. So it's a Jupyter notebook. You'll run that notebook, and if the whole notebook goes through and runs, then you are ready to go. Your environment is set up correctly. So I'm going to start with the QML classifier challenge. So the structure of this challenge is as follows. We are going to give you, or we do give you, a data set that from this paper, Havlicek and al., published in 2018. It's the same data set used there. And you're going to implement a variational quantum classifier that trains a model over that data set and then tests at the highest accuracy possible. We've provided a template for you. So if you go to QMA challenge, EQC challenge, what we've done is provided a template for you that trains at about 50% accuracy. So it's a binary classification task. And the way that the notebook is currently set up is a non-optimal implementation that you are going to modify and adapt to solve this problem in the most optimal / accurate way possible. So here's an example of the classification data set. I'll go through a little bit later on in the talk about how this data is generated, but it can be found in the file genbinary.py is where the data is generated. So this is your classification data set. We walk you through a number of the steps about what kind of goes into creating this variational quantum classifier. We define a number of functions that are that implement the quantum circuit that's going to be contain the trained parameters that will be optimized in this model. And we've done so in a way that each of these to-dos marks a function that needs to be modified. So we have a feature mapping function, an onsats that's defined, and then overall circuit circuit function, all built in Penny Lane, that each need to be adapted to kind of implement this binary classifier in the correct way. After this, we've inserted a number of functions here that kind of emulate the training procedure used in the original Havlicek paper. So these don't need to be modified at all. You can leave these, or you can modify them if you want to, if you see any benefit in doing so. And then what we do is we go through gradient descent procedure using the model that you have, or the circuit, the parameterized circuit that you've implemented to train its weights. And then ultimately, as you can see in this one, there's no convergence towards a minimum, or no kind of improvement of the model over time. This is going to be your job, is to implement a circuit that does so. At the very end of it, you'll be asked to interact with quantum hardware through the Amazon Brockett Penny Lane plugin. So here we've given you a bunch of devices you can choose from. There's more devices that you can find on Amazon Brockett supported devices. You're going to define that device, and then you're going to test your model on that remote device to see exactly how accurate it is. And then you'll be able to, at the bottom here, to see kind of what the classifications were that your model made, and then make improvements on it from there. So the structure of this challenge is a little different than a regular hackathon challenge, in that it accepts submissions on a rolling basis. Each team is allowed one submission per day. So in a normal hackathon, you work through the duration of the time to kind of perfect your model and then submit at the very end. We're keeping a live leaderboard that'll basically keep track of the highest performing models throughout the duration of the hackathon. So if you implement even a model that performs at 70% in the next 24 to 48 hours, you can go ahead and submit that and then get yourself ranked on the leaderboard. Maybe you'll jump straight to the top, and then continue to work on your solution as other people continue to push their submissions as well. So this will be kind of a cool way to see how your model stacks up, and will hopefully generate some buzz and be a bit of fun. There's lots of resources linked here that are intended to help you get started using Penny Lane, using qBraid, and using the Amazon Broadcat plugin. And I'm going to go through some of those resources in the middle of my talk, but you're welcome to peruse through all this, and there's tons of info that is intended to help you carry out this successfully. The qBraid Open Challenge is much more open-ended. You are going to have the ability to kind of choose your own destiny here and submit a project that on a topic that's interesting to you. The only requirement is the use of the qBraid SDK. So there's just one submission for this challenge at the end of the hackathon period. In this challenge notebook, we provided just a small little template. So enabling quantum jobs, which is a requirement, and then doing some of the imports to the qBraid SDK. And then using some of the SDK's features, including the transpiler and some of its device interfacing functionality. You're just going to work that into a cool project or application that that you find most interesting. So we've provided a bunch of resources here as well, including the SDK user guide, which I highly recommend. Some of its reference docs, and then some of the demos as well. So that is it for a rough challenge overview. If I don't have any questions up to this point, I'm going to dive back in to my slide deck, and I'm going to give a super brisk kind of overview of what is quantum machine learning and kind of where are we starting in this VQC challenge. So depending on your background, you may or may not be familiar with quantum machine learning. Quantum machine learning just is exploring many of the same ideas that are present in classical machine learning, but just in the context of a quantum device or quantum computer. Many of the algorithms today that are interesting to explore are focused on some of these near-term quantum devices, but in the future, applications and algorithms for universal quantum computers will be super interesting to look at. You can use quantum computers like neural networks. They can be trained in a very similar fashion as neural networks to solve familiar tasks like image classification, linear regression, in a lot of the same ways that classical machine learning algorithms can do. So by systematically adapting some of these physical control parameters on quantum hardware and other quantum devices, such as electromagnetic field strengths or laser pulse frequencies, you can adapt these kind of the parameters of a quantum circuit to kind of optimize it to a particular task or problem. So quantum circuits are differentiable, which is kind of what makes them well suited for machine learning. So differential programming is where algorithms are not hard coded but learned. And this comes back to parameterized circuits and this idea of kind of updating the circuit that you're using iteratively as you learn more about the problem that you're trying to solve, and kind of adapting your circuit implementation in this way. So this brings us to quantum neural networks. So quantum neural networks are kind of synonymous with variational or parameterized quantum circuits, and the idea is that they consist of gates that have some type of dependency on angles of parameters that are kind of systematically updated by the person that's using the circuit. So just like in classical machine learning, where you'll update the weights associated with many of the nodes in a quantum neural network, or in a classical neural network. In a quantum neural network, you're updating circuit parameters. So variational circuits or parameterized circuits have three main ingredients. They start with a preparation of a fixed initial state, as many quantum algorithms do. Next, you're going to have your quantum circuit. You can call it U theta. That's parameterized by a set of free parameters, theta. So this is kind of the essence of a parameterized circuit. And then finally, you're going to have the measurement of an observable. So then we can further zoom in and look at kind of like what makes up this U theta. You know, what process do we use to update these free parameters, and what other components kind of go into creating a variational circuit that solves a machine learning problem. So starting with the free parameters, we have to figure out in what way we want to modify them. We have to establish some type of cost function. A cost function in machine learning is basically an evaluation of how accurate your model is at that given point. So by evaluating the expectation value of your circuit with a given set of free parameters, you'll use this to kind of construct a cost function that is proportional to, or that'll be able to that you'll be able to use to determine how accurate your circuit is for a given task. Cost functions can take many different forms, and we've outlined one for you in the qBraid-HAQS challenge. But the basis of them is that they are highly dependent on these free parameters, which are then going to be iteratively tuned to kind of minimize this cost and maximize the accuracy. Variational circuits and variational classifiers also have fixed parameters or non-adaptable parameters. So these are what are used to encode the data. So one of the big differences between classical and quantum machine learning algorithms is the necessity to kind of convert the classical information that is given to you as data to input into quantum information. So you have to somehow convert this classical data into a quantum state. There's a number of different ways to do this. There's basis encoding, there's amplitude encoding, but the process through which you do it is going to be very important to the performance of the algorithm as a whole, and the accuracy of your overall model. So to kind of recap, variational quantum classifiers are quantum circuits that can be trained from labeled data to classify new data samples. And as we just touched on by the end, it's kind of, you could think of them as the combination of two variational circuits. So the first circuit associates gate parameters with fixed data inputs. So this is where you're getting the input data and you're encoding the input data into a quantum state that takes the form of quantum gate parameters. So this is like the first half of the circuit. And then the second circuit is where you have your free or trainable parameters. So after you've kind of mapped your classical data into a quantum state, then you are going to optimize your trainable parameters in the second half of the circuit towards your machine learning task. Yeah, so instead of continuing on these slides, I think it's probably, let's see. Yeah, so this is probably actually a good time to jump back to our HAQS notebook and point you towards this VQC tutorial that is taken from Penny Lane, and to kind of like put some of these abstract mathematical terms into code. So in this variational classifier tutorial, which can be found VQC_tutorial in the HAQS challenge, it walks through two different implementations of a VQC, one for a kind of a toy example for binary classification, and then the other which trains an example over the iris data set. So at first, we're just going to solve, use a quantum classifier to reproduce a parity function. So some function f that classifies a data input as 1 if it's uneven or 0 otherwise. So the first step of the quantum of the variational classifier, right, was these fixed data inputs and the mapping of the fixed parameters. So taking classical data into quantum data. So that's done right here in this state preparation function. So the quantum state after preparation is a computational basis state where that has ones where x has ones, for example, here. So this is yes, this is basis state preparation where you're taking a classical data point and you're kind of transforming it into a quantum state. And then the next step is right using the free parameters. So this is where we've implemented a layer that encodes a number of rotation gates, each of which is rotating with order of magnitude determined by some free parameter which you initialize and then will eventually update according to how the cost function is updated. So now we can very clearly see these two steps of the variational circuit taking form here, first in the state preparation, and then applying some weights to a number of layers that encode the free parameters. And then here we're taking the expectation value again in the Z basis, and this is equivalent to kind of the cost function that we had talked about at the very end or the very beginning. So down here, we are just defining some functions that take this expectation value and use it to compute a square loss. We're further using that to compute a % accuracy based on the loss that was calculated. And then finally, we're updating these free parameters that we've defined over a number of training iterations to eventually build a classifier that is able to basically implement this parity function in a quantum algorithm. Down lower in this tutorial, they further apply this to an iris classification task, which takes the same idea and applies it to a more complex example, and this will be useful in the actual VQC challenge. This will be uses amplitude encoding, which is what you will use in the VQC challenge. And I encourage you to kind of go through this notebook and make sure that you understand it, and then you'll find that a lot of the concepts that you see implemented in this notebook will be directly translatable to the VQC challenge and allow you to kind of have a good starting point for where to begin your implementations. All right. So finally, I think I'm doing okay. So for the qBraid Open Challenge, some of you might not be familiar with the qBraid SDK. So to kind of give context for this challenge, I'm just going to run through a quick demo of the SDK, and hopefully that'll maybe stir up some ideas for where you might take a project or what you might do. So I'm in the qBraid Lab demo repo right now, which is public, so you can go and find these notebook examples there. So the SDK is broken into two main layers, and actually our user guide is a good example of this. So on our docs page, in our user guide, you'll find circuits, devices, and jobs layers of the SDK. And each of these kind of like layers in abstraction, the SDK, are meant to provide an interface between many different front-end quantum software building libraries. So we support Cirq, PyQuil, Qiskit, Brocket, and PennyLane on circuit building layers, as well as device layers, and from that, quantum jobs layers. So the transpiler focuses on the circuit building layer of these quantum software packages. So what we do is we provide, through the SDK, a circuit wrapper, which can be used to transpile circuits built in any of these languages into any other language. So for example, if I was to build a circuit in Qiskit, simple circuit using many different of the gates available in Qiskit, I can then apply the qBraid circuit wrapper to the Qiskit circuit, and then using the .transpile method, and by specifying a different quantum software package, the target package that I want, so in this case Brocket, I can immediately transpile this Qiskit package into Brocket. If I was to use the same wrapped circuit, so the same circuit wrapper object, and transpile it to Cirq, I'll then immediately have the equivalent Cirq circuit, and PennyLane and PyQuil follow the same form. So these transpilations are able to be done in either direction and between any of the packages. So out there, you may see a lot of these different plugins that allow you to interface between the hardware from one package to the backend of another. And while these are convenient, the qBraid SDK provides a really elegant, slick way for you to transpile these circuits yourself on the front end, and do so just using one consistent format and like protocol to kind of convert these circuits. So it's extremely robust. So we support, I think, almost all the gates that are available in each of these libraries. And when a gate isn't found, instead of throwing an error and kind of exiting the program, we actually decompose it we convert it to a unitary and decompose it into smaller gates, so that every transpile is going to go through kind of no matter the complexity of the circuit. And this is one of the big, this is like the utility kind of the qBraid transpiler over many of the other quantum software plugins that you may find. So next we have the device layer. So I found in my own time as a quantum software developer that knowing what devices are online kind of and what the procedure is to see if they're available and like what their job ID is, and then apart from that, even the exact protocol to create a device like objects is different between every quantum software package, and it's very confusing, especially when you just have a single kind of objective use case in mind. It requires, adapting to a lot of these different languages, syntax, and kind of formulas for implementing, interacting with these APIs and getting the device objects. So the qBraid SDK, we have this get devices function, which prints a really nice kind of table that lists the supported devices over a bunch of different vendors, from simulators to QPUs, and even tells you if they're online or not. And we use a qBraid ID, which kind of is just a simple adaptation of the regular device ID, but allows you to use a similar form of the circuit wrapper, which is the device wrapper. So before I get to that, these are just some examples of filters that you can use to kind of search for specific devices. For example, looking for a device that is a simulator that has state in the name between AWS and IBM, or a QPU with at least 5 qubits that's online. You can use these kind of this querying syntax to find devices. And then down here is where we define or import the device wrapper as well as the job wrapper. So the device wrapper is used in the same exact way as the circuit wrapper, but you're just passing in the qBraid device ID that you find in the above table. And immediately you have a device-like object that you can use to run a quantum program. So we give you a lot of the information about the device right off the bat from the .info attribute. We take care of kind of the configuration of credentials and allow you to submit circuits to that device that aren't even necessarily in the same language. So for instance, if I develop a circuit using the qskit package, but I want to submit it to like the circ density matrix simulator or the AWS density matrix simulator, I can go ahead and use that same syntax. So here I used the IBM Q device and I ran it on the qskit circuit, which makes sense. But down here, I'm applying the same device wrapper to the Google device and able to run that qskit circuit on the Google device, run the qskit circuit on the AWS device. So it's really convenient not only for finding devices, instantiating the device-like objects, but also to sending circuits and kind of allowing the transpiler that we looked at in the first notebook to kind of operate behind the scenes and transpile your circuit in real time before sending it off to the device, and saves you a lot of time and effort. It's very convenient. So similar to the get devices function, we have get jobs. So this is kind of a way for you from a Jupyter Notebook to get a list of your most recent jobs with qBraid job IDs. And then we kind of extend the abstraction of circuit and device wrappers into job wrappers. So using job.result, we can get the results for each of the jobs, no matter if it was a Google, AWS, or an IBM job. It's the same syntax, same formula. Get the measurement counts, and then we do post-processing on the measurement counts to put it in a consistent format with consistent data types that allow you to compare results between backends. This is great for benchmarking. It's great for instances when you change the device used by a program on the fly. The code that comes later won't break because you know that the result format is going to be consistent. So this kind of universal interface on the circuit device and job/result layers is what kind of sets the qBraid SDK apart, and it makes it kind of a great starting point for implementing a lot of different quantum algorithms as a tool for a quantum software developer in general. So that is going to wrap up my my challenge overview / brief survey of VQC and the qBraid SDK. And at this point, I would be more than happy to take any questions that people have about the challenges or just other topics.
All right, thank you so much, Ryan. We do have a few questions, I think. Let me double check on those. Yes, we have, I think. Questions and answers. I think it's on here. If people could put it in the talks chat, that would be great. This is all the challenges we have. Andy Krinya, one. I'm sorry if I butchered your name. And there's one clarification by Sis Theta. Does the accuracy that matters for the first challenge, is that correct? Does one need to stick to the instructions in the notebook?
So yes, it's the overall accuracy that matters. And do you need to stick to the instructions in the notebook? So let's see if I can go back to this challenge repo. So yes, your classifier will be evaluated based on how it performs on for the given machine learning task, and that's based on the accuracy against the test set, right? So this is your training test data, right? And you've 150 training data points, 50 test data points. At the end, you're going to evaluate your model against the test data points, and the number that it gets correct out of the test set is going to be the accuracy of your model, and that will determine the place that you rank on the leaderboard. Whether you need to stick to the procedure or the kind of outline of this notebook, no, you don't. So this is simply a template, and if you want to kind of use an entirely different kind of VQC structure or approach, then that is completely valid, and we would encourage you to do that. This is simply provided as kind of a starting point for people that may not know exactly where to begin, but for people who are experienced in QML and have an idea of what they would like to do for this problem, then I would encourage them to, by all means, implement their own functions and use their own training protocols, and you can kind of disregard some of the others that are here.
Thank you, Ryan. And we also have one more question, which is, I think, an excellent question by Harold Kimmy. Can TCAT, so this is the Quantinium package, be installed, which optimizes quantum circuit code and almost doubles the amount of circuits that can be simulated?
Let's see, is TCAT Python based? I forget, is that a pip install, or is TCAT have C dependencies as well?
I think there's the PyTCAT version as well, so
yeah,
you could maybe.
PyTCAT, yes. I'm not overly familiar with the TCAT package, so I'll have to look into that more. But in general, I can just answer the question. Let's see, desktop 3. Sharing this one. Am I sharing my screen right now? Ricky, am I sharing my screen right now?
Yep.
The HAQS22 one? Okay. Where's qBraid Lab? So in general, yes, packages can be installed. In addition, let me show you how you do that. While this is loading, Ricky, do you have another question that I can answer?
Yes. Alex Khan has a question about what is the difference between running an ML job on Pennylane versus Brocket? Is a challenge using a simulator only? So 2 questions.
Yes. Okay. So, so the difference is going to have to do with, well, from a programming perspective, we've shown you kind of how to instantiate both types of devices. So here's a local device, and then down a little lower, we have an example of how to implement the Brocket device. But when you're running a local simulator, this is just running a simulation of a quantum computer on your local machine. So it's going to be running on, I guess, the qBraid cloud, the CPUs associated with the qBraid cloud when you're using the local simulator. And when you're using a remote Brocket device, whether that be an IonQ or a Getty device, you're actually running your program on that quantum hardware itself. And this is enabled through the qBraid quantum jobs CLI. So by enabling quantum jobs, we're basically creating a path to send jobs to those quantum computers that are available through AWS, kind of like right off the bat. So we encourage you, just because of kind of how big these tasks are to run, And quantum machine learning algorithms also usually take a lot of time to train. So we encourage you to do your training on a local simulator. So for here, we create a local device that allow you to kind of do your training protocols really quick and find some parameters that may work well. And then when you're actually testing your device or testing your model, now we're creating a remote, we're interacting with a remote Braquette device. And so here we're doing it on the state vector simulator available through Amazon Braquette. And we're actually using parallel execution of the SV1 simulator. But you can use any of the other Amazon Braquette supported devices and follow the PennyLane Braquette tutorials that are linked at the top of the repo to see the different ways that you can send jobs to each of these devices. Let's see. So now that qBraid Lab has loaded, so there's a question just before this about how you may, like, if you can install additional packages. So to see the packages that are currently installed, use your HAQS panel, click on more, and then here's a full package list of everything we have installed. So, you know, I could look up NumPy and see what NumPy version I have. If I look for TCAT, I can see I don't have TCAT. So what I can do is come over here to the qBraid CLI. I can type qBraid EMS, which gives me qBraid EMS list, which gives me a list of my installed environments, and then qBraid EMS HAQS or activate HAQS. This activates my HAQS environment, and now I can do a pip install of PyTCat, I think, and that will pip install that package into that environment. And then after that's done, then I can just click on the more tab again, and then you should see that the HAQS or the PyTCat package now has been added. Yeah, so I should take some minute, but yeah, so then you should be able to go in there and then use the PyTCat package right away. There we go. PyTCat, yep. So now PyTCat 1.7.3 is in my HAQS environment. Other questions?
Thank you, Ryan. We have, I think, one more question. Glad that you can use PyTCat. That's probably going to be pretty useful if you want to optimize your circuits. And then Maha Metawe has asked a question with regards to PennyLane. PennyLane has a bunch of APIs for data encoding. Can we use them?
Yes, you can use all of the APIs that you want to. Absolutely. If they are yeah, anything that requires a credential to access via PennyLane, we don't provide explicit support for. So you're going to have to have your own kind of you know, if it interacts, if anything that you're doing interacts with the Xanadu cloud, then that'll have to be taken care of on your own. But if it interacts with AWS, then all that credentialing is handled for you, but nothing is off limits in terms of PennyLane or any external packages that you may choose to use to implement your solution. Nothing's off limits.
Great. I think we'll get started with the Discord section. So if you guys have any questions that you are working on these challenges, do let us know. Let me double check that we don't have any other questions. Since I missed this, Harold has once again asked if there's a differentiation between the qBraid and the Google Colab environment. Can you kind of illustrate the difference, Ryan?
So between the qBraid and the Google Colab environment, just in terms of, so let's see. Yeah, so I'm actually not as familiar with Google Colab and its features as Ricky is. Maybe Ricky would be better answering this question. I know that there's a lot that differentiates it, but in terms of the features that stand out about Colab that he might be wondering about, I think he might answer that better.
Absolutely. I think the main difference about Google Colab and qBraid is that one is notebook based and one is lab based, where we are lab based. And secondly, even in a Google Colab environment, you're going to still have to deal with a certain Python version where your Python packages may or may not install correctly. And it's very actually difficult to kind of debug that. So it's not as apt for doing like having a whole file system and just like installing things and having multiple environments. Secondly, we provide you a lot more flexible CPU where I think they kick you off as soon as you are no longer using it if you're on the free version. And another great thing is we have a lot more of a robust Git functionality. So if you are doing a whole Git repository, the way that you do it through Google Colab is you copy the notebook and then they kind of take care of that copy notebook. Then you actually make a push, but it's a little bit less developer friendly compared to just using like a Git clone functionality or our terminal that's available. Again, we're a lot more quantum focused because we also have the qjobs as well as just quantum docs and tutorials that are all available, which are not through Google Colab. We have another quick question from Abi, where Abi is asking if to clone the repo, should we set up our GitHub public keys on the environment? And will they be persistent even after restarting the lab?
Yes, you can feel free to do that. You can set your public keys or not. And they will persist after lab. Just as a general rule, everything that is kind of a local install, so anything installed into the /opt or any folder that begins with the slash is going to be kind of erased after install, but anything done locally, so like .local or any other pip installs that are done for the user will be persisted. So in terms of storing GitHub keys, yeah, it should definitely be able to do that. And yeah, so for owning the repo and doing that, you should be fine for sure.
Thanks, Ryan. That's really wonderful. And I actually want to add that, that functionality of storing information is not quite available in Colab. As someone who has used Colab before, you have to mount your Google Drive, which is not difficult, but then you have to kind of understand the file system of a Google Drive and how it updates, which is more difficult. Sometimes things get erased and stuff. So I would recommend also, again, qBraid has that file system available for you. It persists, and that's also a great feature.
So we have a question from Mohamed Metowe regarding qBraid. In a previous hackathon on qBraid, experienced frequent kernel disconnection death. Does it mean that my circuit has to be optimized? Thank you so much for this question. We have done a lot of work on qBraid Lab, and this should be we've really done a lot of work to kind of eliminate this problem. And hopefully in this hackathon that this won't come up. If it does come up, then please put it in the bugs channel on the Discord. But no, you should not at all have to kind of cater your program to work around this bug. We will be taking care of it as it comes up, but as lab exists right now, we hope that it doesn't come up for anyone. Yeah, that's
great. Thank you, Ryan. I think I might have one more question. Okay, yes. And again, everyone, if you guys could ask these questions from Zoom, that would be great. I think it's the first day. We all are just kind of getting acclimated, even ourselves, as this is our very first time running hacks. But once again, thank you guys so much for attending Hacks. If you guys have any further questions, we will be doing Discord office hours for the next 2 hours on getting started with qBraid, asking questions about the challenges. If you run into any bugs, we'll also kind of take care of those as well. And next week, be prepared for some awesome stocks, starting with Rajiv Krishna Kumar from Goldman Sachs, speaking about how they are looking at quantum computing, which is going to be super exciting, alongside several other speakers on Monday. And then on Wednesday, we also have great speakers as well, starting off with, I think, Elvira from BMW and a few other corporations that are working on quantum computing as well. So once again, if you guys have any questions, just let us know. We're always here for you. And thank you guys for using qBraid. And good luck on the hackathon. We'll update you guys shortly on prizes and a lot more. All right. We'll close in a minute. Thank you guys. Song recs are recommended as well.